13 Depths You Won't Survive. Welcome, curious reader. Before you turn the page and embark on your journey downward, there's a warning that's typically given just once. This guide is unlike those you find in airports next to magnets and beach towels. You will find no advice on the best restaurants or comfortable hotels. There are no 5-star ratings here because the places we'll discuss assign only one category to their visitors: permanent. Light does not reach these depths. Maps here are merely suggestions, and those who crafted them by hand often returned with something that's hard to explain in words, or they never returned at all. If you're reading this and thinking, "Sounds interesting, I want to go there," that's precisely the warning signal psychologists have cautioned about. Be sure to like and save this article. By the end, you'll be glad you did so over sushi. Depth 1. The Challenger Deep, a bottom that gazes back. There are places on the planet that allure precisely because of their extremity, not despite being deadly, but because of it. The Challenger Deep in the Mariana Trench is one such place. Located in the southwestern part of the Pacific Ocean, approximately 300 kilometers southwest of Guam, it represents the deepest point of the world's oceans, measured with enough accuracy by humans. The depth of this spot is about 10,900 meters, nearly 11 kilometers down from the water's surface, which you see from the deck of a ship, squinting in the tropical sun and thinking you're not drinking enough water. To grasp the scale, if you take Mount Everest, 8,849 meters above sea level, and lower it straight down to the bottom of the Challenger Deep, its peak would still be about 2 kilometers below the water's surface. This is not hyperbole or a poetic image. It is simply the geometry of the planet, which at some point decided that deep is a concept requiring radical rethinking. From the surface, the Mariana Trench looks like any other ocean. No whirlpools, no ominous bubbles, no hint that right beneath the keel of your ship lies the most monstrous depression on Earth. The water is blue. The sky is blue. Somewhere in the distance, birds fly. This is nature's classic deception, perfected over millions of years of evolution to absolute perfection. The ocean here is so pristine and outwardly welcoming that it seems ready to embrace you, forever and without a refund. The Mariana Trench formed as a result of subduction, a process in which the Pacific lithospheric plate slowly, yet inexorably dives beneath the Mariana Plate. This process has been ongoing for tens of millions of years. The bottom of the trench continues to deepen, approximately 2 centimeters per year, which, on geological timescales, is akin to someone diligently and methodically digging a hole, knowing neither fatigue nor reason. Geologists refer to such zones as subduction trenches. Lovecraft, upon reading this description, would likely have simply nodded and jotted it down in his notebook. Now let's talk about what exactly happens to you if, somehow, you find yourself at the bottom of the Challenger Deep without proper equipment, meaning without a submersible capable of withstanding pressure of 1,080 atmospheres. The number 1,080 may seem abstract until you realize that sea level pressure is precisely 1 atmosphere. At the bottom of the trench, the pressure is 1,080 times greater. This means that every square centimeter of your body would experience a force of 107 kilograms. This is not heavy. This is instant and complete. The human body, despite its remarkable adaptability, is not an object designed for compression. It is designed for something entirely different. Aside from the pressure, there is total and absolute darkness, true darkness that poets have written about in metaphors, unaware it exists literally. At a depth of about 200 meters, sunlight completely vanishes. Below that is the zone of eternal night, where even the concept of color loses its meaning, because perceiving color requires light, and there is none here. The bioluminescence of local creatures are the only lights in this world. And these are not romantic fireflies. These are lures for predators, mating signals, and danger warnings written in a language humans misunderstand. The water temperature at the bottom of the Challenger Deep hovers around 2 degrees Celsius. This is a bit warmer than you might expect from the absolute abyss, and it is due to geothermal processes in the crust, the very subduction mechanism that created this trench. Nonetheless, 2 degrees is not cool. It is deadly cold, disguised as a moderate temperature that kills slower than the pressure, but no less surely. The history of the exploration of the Challenger Deep is a tale of human stubbornness multiplied by engineering genius and a fair dose of recklessness. The first reliable measurement of the trench's depth was taken in 1875 by the British research vessel Challenger, after which the abyss was named. Scientists used a regular cord with a weight that was sufficient for about 8,000 meters and still could not reach the bottom. This discovery made an impression on the Victorian era, similar to the realization that your apartment is smaller than you thought, but on a planetary scale. A real breakthrough occurred in 1960 when Swiss oceanographer Jacques Piccard and U.S. Navy officer Don Walsh made a dive in the submersible Trieste to the very bottom of the trench. They reached a depth of about 10,910 meters, an absolute record that lasted for decades. The dive took about 5 hours. They spent 20 minutes on the bottom. 20 minutes! To feel that they were at a point reached for the first time in the history of humanity, before ascending back up for another 5 hours. Piccard later described that the porthole of the submersible began to crack at a certain depth, making a sound he compared to the explosion of a gunshot. They continued their descent. This is what's called scientific daring, or, in less polite terms, something else entirely. In 2012, director James Cameron, the same one who made Titanic and Avatar, descended alone to the bottom of the Challenger Deep, in a craft of his own design. Cameron spent 3 hours there. He described the ocean floor as a lunar landscape, completely flat, covered with layers of soft sediment several meters thick, in which his craft became stuck upon landing. This sediment is the result of millions of years of organic particles falling from above, the remains of plankton, dead cells, and rock fragments. All of this slowly accumulated on the seafloor, creating a layer that scientists poetically refer to as marine snow. Cameron was disappointed. He expected to see a thriving ecosystem teeming with life, but found practically a desert, which, however, does not make this place any less deadly, just deadly in a different way. Life at the bottom of the Challenger Deep does exist, and that alone is so strange that it's hard to believe without scientific evidence. There, researchers have discovered single-celled organisms called foraminifera, measuring several centimeters, gigantic by single-celled standards. Amphipods, shrimp-like crustaceans reaching lengths of 30 centimeters, inhabit that depth. Polychaete worms and nematodes have also been found. All these creatures have developed adaptation mechanisms to withstand pressures of over 1,080 atmospheres, which scientists continue to study with unabashed admiration. Their cell membranes are fundamentally different from those of surface organisms. They contain special molecules that prevent compression under monstrous pressure. Nature, as always, found a solution where humans see only a dead end. In 2019, American explorer Victor Vescovo completed a series of dives in his vessel, the Limiting Factor, setting a new depth record, 10,928 meters. During one of his dives, he discovered a plastic bag and a candy wrapper on the sea floor. Researchers refer to this moment as one of the darkest symbols of modern times, the deepest point on the planet, unreachable by most people and most technologies, was found to be polluted by human trash before it was truly studied. If there is any irony in this, it's of a kind that provokes no laughter. The Challenger Deep is not just a depth. It serves as a philosophical argument in the debate over how much humanity is capable of understanding the planet on which we live. We know more about the surface of the Moon than we do about the bottom of the Mariana Trench. We have mapped Mars with meter-level precision, yet the depths of our own ocean remain a blank spot on the maps. This isn't a rebuke. It's simply a statement of how inaccessible the abyss is. Space takes through vacuum and radiation. This abyss takes through pressure, darkness, and temperatures near absolute zero. Both options kill with equal effectiveness, but at least the cosmos is visible to the naked eye. Leave the Challenger Deep alone. Not because it will reject you, no, it will welcome you eagerly. It's just that it won't be the kind of hospitality you were expecting. Now, let's rise a little higher, just a bit, and move to where the water appears innocent, smells of sulfur, and the temperature can scald you alive without any prior warning. The next depth awaits, and it has a name that sounds almost beautiful. Depth 2. The hydrothermal vents of the Mid-Atlantic Ridge, the underworld that boils from within. Picture a place where the Earth literally breathes, where columns of superheated water, the color of anthracite, burst forth from cracks in the seabed, black, dense, resembling smoke from factory chimneys, but just 2.5 kilometers beneath the surface of the Atlantic Ocean. Where the water temperature reaches 400 degrees Celsius, 4 times the boiling point under normal atmospheric pressure, yet the water doesn't boil, as the monstrous pressure of the depth keeps it in a liquid state, as if nature invented this trick to defy all intuitive notions of physics. This is the Mid-Atlantic Ridge, a submerged mountain range approximately 18,000 kilometers long, stretching through the entire Atlantic Ocean from north to south, and one of the most geologically active regions on the planet. Here, the Earth is not just existing, it is being born right now, right beneath your feet. Only those feet are 2 kilometers of water. The Mid-Atlantic Ridge is the boundary of 2 lithospheric plates, the North American and Eurasian plates to the north, and the South American and African plates to the south. Unlike the Mariana Trench, where one plate dives beneath another, here the plates are pulling apart, about 2.5 centimeters per year. This doesn't sound impressive until you realize that this very process has created the entire Atlantic Ocean over millions of years. Once, North America and Europe were a single landmass, part of the supercontinent Pangaea. Then the plates began to drift apart. Now, there are 3,000 kilometers of water between them, and an ongoing geological cataclysm occurring too slowly for human perception, but nonetheless grand. In areas where the plates separate, cold ocean water seeps into the seabed. It filters through cracks in the basalt, descends toward magma chambers where the temperature is measured in thousands of degrees, heats to the extreme, and gushes back out through the vents of the hydrothermal sources. Along the way, it becomes saturated with dissolved minerals, sulfur compounds, manganese, iron, copper, zinc. When this superheated mineral-rich water meets the cold surrounding water, the minerals instantly crystallize and settle, forming tubular structures, so-called black smokers and white smokers. The black ones are due to iron and manganese sulfides. The white ones result from calcium carbonates and silicates. Some of these chimneys reach heights of 60 meters, true Gothic spires of underwater cathedrals, built not by architects, but by geochemistry. Black smoker sounds almost poetic. In reality, it refers to a pipe with a diameter ranging from a few centimeters to several meters, from which a jet of water erupts at a constant speed, with temperatures between 300 and 400 degrees Celsius, saturated with acid and having a pH level around 2 to 3. For comparison, vinegar has a pH of about 3. Lemon juice is around 2. You probably wouldn't enjoy diving into lemon juice at 400 degrees, although if you've read this far, the question of whether you would enjoy it has likely ceased to be the main concern. The first hydrothermal vent was discovered in 1977 on the Galapagos Rift, not the Mid-Atlantic Ridge, but the same principle, the same geology, the same architectural design of nature. The research submersible Alvin, the legendary deep-sea vehicle from the Woods Hole Oceanographic Institution, descended to a depth of 2,500 meters and found something that literally changed biology as a science. Where, according to all theoretical calculations, there shouldn't have been any life, no light, no organic matter, and no usual source of energy, life was bubbling. Tube worms up to 2 meters long, giant white crabs, mussels the size of a palm. All of this thrived in close proximity to boiling acid and in complete darkness. The discovery was revolutionary. Until then, biologists firmly believed one thing. All life on Earth depends on photosynthesis, the process of converting sunlight into organic matter. Plants do this directly. Animals eat plants. Everything else is a consequence. Hydrothermal vents completely disprove this postulate. Here, the foundation of life is chemosynthesis. Bacteria use the energy from chemical reactions, the oxidation of sulfur-containing compounds, instead of sunlight. These bacteria are the basis of the food chain. They are eaten by worms. The worms are eaten by crabs. This is a parallel biosphere, existing entirely independently of the Sun, and seemingly formed back in the Archean era, 3.5 billion years ago. This is why astrobiologists today study hydrothermal vents on Mars or the moons of Jupiter and Saturn with special interest. Life that does not rely on the Sun could well exist there. But let's return to what specifically kills a human. The list is impressive in its breadth. First of all, pressure. At depths of 2,000 to 3,000 meters, where most of the known hydrothermal fields of the mid-Atlantic ridge are concentrated, the pressure ranges from 200 to 300 atmospheres. This is beyond a little uncomfortable. It is immediate and final for an unprotected human body. Then there's temperature. Near the orifice of a black smoker, the water is heated to 400 degrees. 10 meters from the vent, it's already about 2 degrees above 0 Celsius. This temperature gradient is so sharp that in some research apparatuses, temperature sensors displayed both values almost simultaneously while the device slowly moved along the field of sources. Then comes chemistry. Dissolved hydrogen sulfides are lethally toxic. Sulfuric acid in water is aggressive towards metals, let alone biological tissues. And finally, geology. Vents are active while they are active, then they fall silent, sometimes quickly and without warning. This is called vent collapse, and it is accompanied by the eruption of a huge amount of superheated water and debris from the pipe. For research apparatus in close proximity, this is akin to an explosion. The Lost City Field is one of the most studied and also one of the eeriest hydrothermal complexes of the Mid-Atlantic Ridge. Discovered in 2001 by a team of scientists aboard the research vessel Atlantis, this field is fundamentally different from black smokers. There is no black smoke or boiling acid here. Instead, there are towering white spires of calcium carbonate resembling a Gothic cathedral submerged in eternal underwater darkness. The white smokers of the Lost City Field emit water with a temperature of only about 100 degrees Celsius. This is boiling water, but alkaline, with a pH of around 11. For comparison, ammonia has roughly the same level of alkalinity. Some towers reach 60 meters in height and are estimated by scientists to have existed for over 30,000 years. They are monuments of deep-sea architecture, but instead of architects, there is geochemistry, and instead of tours, there are robotic devices with cameras. The Lost City fascinates astrobiologists for a special reason. Alkaline hydrothermal sources of this type are considered the most likely place for the origin of life on Earth. Conditions are created here where simple inorganic molecules can spontaneously combine into more complex organic chains, the precursors of amino acids and nucleotides. In other words, this place looks as though something significant happened here that ultimately led to your existence. This should evoke a sense of reverence. Instead, it somehow stirs a slight existential anxiety. The history of research on the Mid-Atlantic Ridge is full of episodes that, when recounted, sound like plots from horror movies directed by a realistic filmmaker. In 1974, the Soviet-American expedition FAMOUS, short for French-American Mid-Ocean Undersea Study, conducted a series of dives in the bathyscaphs Sienna and Alvin along the Rift Valley of the ridge. Researchers saw the living, active rift zone with their own eyes for the first time, not through hydrophones or seismographs, but through portholes at a depth of 2,500 meters. What they described defied familiar language. Dark basalt fields covered with pillow lava, characteristic rounded mounds of solidified magma. Cracks that extend downward to an indefinite depth. Sounds. A quiet, constant cracking of cooling rock. One of the expedition members, French geologist Xavier Le Pichon, later wrote that at one point he had the feeling that the apparatus was watching him. Not the vent, not the rock, but the place itself. In 2006, the research device Hercules, operating autonomously in the Snake Pit hydrothermal field on the Mid-Atlantic Ridge, recorded a series of seismic events right during its descent. Operators aboard the vessel clearly heard through the hydrophones sounds that participants described as pops and grinding, either the activation of a vent or a slight collapse of the pipe. The device was pulled to the surface prematurely. Upon inspection, they found that one of the cameras was covered with a layer of sulfides, meaning the device had come significantly closer to the source than planned. No one was hurt, but discussions about this continued among the team for several days. There are hydrothermal fields on the Mid-Atlantic Ridge that are officially mapped and bear names: Tag, Snake Pit, Rainbow, Broken Spur, and Menez Gwen. The last name translates from Breton as White Mountain. The Rainbow Field is located at a depth of 2,300 meters and is distinguished by an unusually high hydrogen content in its emissions, making it, according to some hypotheses, potentially interesting for the search for life forms utilizing hydrogen metabolism. This sounds like a story from Subnautica. You dive to the bottom, find glowing towers, scan them, and the game tells you that creatures live here that you didn't know about before. The difference is that in Subnautica, you can save the game. Here, you cannot. The hydrothermal vents of the Mid-Atlantic Ridge are a place where geology, chemistry, biology, and physics converge at a point that is completely indifferent to human presence. Not hostile, precisely indifferent, which can be arguably more frightening. Hostility implies intention. Indifference does not. This place existed 3.5 billion years before you, and will exist 3.5 billion years after. You are just another organic molecule, accidentally caught in an area of high pressure and elevated temperature. Leave Rainbow and Lost City alone. Not because they are boring, because they are boiling. And now, we rise a little higher and head to where it's not pressure or temperature that kills, but what is in the water. A liquid that looks like water, behaves like water, but isn't water in any sense you might be familiar with. The next depth is called the Scallop Lakes, and it awaits you at the bottom of the Gulf of Mexico. Depth 3. The Scallop Lakes of the Gulf of Mexico. Water inside water that kills twice. There are natural phenomena that, at first description, sound like an editor's mistake or a failed metaphor. A lake at the bottom of the ocean is one such case. This sounds like the beginning of a bad riddle, or the title of an album by a progressive rock band whose members were overly fascinated by Lovecraft. But this is not a metaphor, and not an error. It is a real phenomenon, documented and studied, yet still one of the most surreal objects on the planet. At the bottom of the Gulf of Mexico, at a depth of around 800 to 1,000 meters, there are actual lakes, with their own surfaces, with their own shores, with waves that form when submersibles move along the edges, with currents inside, with a separate ecosystem around the perimeter, and with the ability to kill almost everything that enters them, quickly, efficiently, and without unnecessary drama. They're called brine pools, derived from the English word brine, meaning salt water. In Russian, they're often referred to as Rapana lakes or hypersaline depressions. The essence of the phenomenon is this. In certain areas of the seabed, enormous deposits of salt are concentrated, remnants of ancient seas that evaporated and were buried under layers of sediment millions of years ago. Under the pressure of the overlying layers, the salt slowly flows, behaving like a very viscous liquid, and in places where the roof of the salt layer breaks through, the brine begins to seep to the surface of the seabed. This brine is saturated 3 to 5 times stronger than ordinary seawater. It is heavier than the surrounding water and does not mix with it, just as oil does not mix with water. It collects in the depressions of the terrain, forming lakes with distinct shores and almost mirror-like surfaces. It looks as though someone took an ordinary lake, covered it with 200 meters of water, removed the sky, and left only the surface, perfectly smooth, slightly glowing in the beam of the research submersible spotlight, reflecting its light back like mercury. When the submersible approaches the shore, the boundary between the brine and the seawater is strikingly clear. It is not a gradual transition but a sharp line, as if someone drew it with a ruler. The French researcher who first captured this on video at the end of the 1990s later remarked that his first thought was, "This is a montage." His second thought was, "We need to take a sample." The Rapana lakes of the Gulf of Mexico were discovered and thoroughly studied starting in the 1990s, although their existence was suspected by geologists even earlier, based on data about salt diapirs characteristic of this region. The most well-known and studied one is located about 200 kilometers south of the Louisiana coast and is informally named the Pearl of the Gulf of Mexico, though that name is used only by those who study it remotely. Those who worked nearby prefer other epithets. The lake's size is about 100 meters in diameter and several meters deep. By the standards of surface lakes, it is a pond, no more. By the standards of underwater anomalies, it is a phenomenon significant enough to have its own ecosystem and reputation. What exactly kills in the Rapana Lakes is a question with several answers, and all of them are correct at the same time. The first and foremost factor is the concentration of salt. The brine is so saturated with sodium chloride, magnesium chloride, and other salts that any marine organism that enters it experiences osmotic shock. Osmosis is the process where water seeks to equalize the concentration of dissolved substances on both sides of a semi-permeable membrane. The cell membranes of living organisms are exactly such membranes. When a cell finds itself in an environment with a salt concentration vastly higher than its intracellular levels, water is literally drawn out of the cell. The cell shrivels. Tissues become dehydrated. This process is irreversible and occurs rapidly. For a fish that accidentally swims into the brine, this means death within just a few minutes, sometimes even faster. The body remains at the bottom or on the shore of the Rapana Lake, osmotically dried out, resembling a marine version of natural mummification. The second factor is hydrogen sulfide. The brine seeping through salt layers passes through strata of organic sediments and becomes saturated with hydrogen sulfide. This gas is toxic. At sufficient concentrations, it blocks cellular respiration by affecting cytochrome oxidase, an enzyme without which cells cannot utilize oxygen. The effect is similar to cyanide poisoning. Cells suffocate even in the presence of oxygen because they cannot use it. For marine organisms that find themselves near the surface of the brine, where the concentration of hydrogen sulfide is at its maximum, this means rapid death. The bottoms of Rapana lakes and their shores are littered with the remains of crabs, fish, and various invertebrates, those that swam too close and did not escape in time. These are the Rapana graveyards, a term used by researchers without any irony, as the place truly looks just like that. And yet, life exists here as well. This is becoming the leitmotif of our guide. No matter where we go, no matter how deadly the place, nature invariably finds a way to thrive. Along the perimeter of the Rapana lakes, at the very border of the brine and normal seawater, bacterial mats exist. Microorganisms that use hydrogen sulfide as an energy source, the very chemosynthetic beings we discussed in relation to hydrothermal vents. They are so abundant here that the line between the Rapana Lake and traditional seawater glows with bioluminescent light, white and orange stripes marking a line of death for some and a line of life for others. Around these bacterial mats, tube worms, mussels, and certain types of crustaceans feed, having developed resistance to elevated concentrations of sulfides. They live literally on the edge, in the most literal sense of the word. The most dramatically documented case of interaction between research technology and a Rapana lake occurred in 2007, when the American research vessel Nautilus conducted a survey of the seabed in the Gulf of Mexico using a remotely operated vehicle. The operator of the vehicle, following the contour of one of the Rapana lakes, decided to test the brine's reaction by lowering the apparatus's manipulator below the surface. The manipulator entered the brine, and the camera captured the moment when the metal arm of the device was inside the lake, covered with a cloudy, whitish crust of crystallized salt. As the manipulator was raised to the surface of the brine, the mirror boundary effect was clearly visible. The liquid did not want to release the arm of the apparatus, not in a mystical sense, but physically, due to the difference in viscosity. A few hours after this maneuver, one of the seals on the manipulator showed signs of corrosion. Magnesium chloride is aggressive towards certain metal alloys. The device was dragged to the surface, the seals were replaced, and work continued. But this episode became a classic example in training materials for deep-sea apparatus operators. Brine eats metal. What it does to biological tissues is a separate and less pleasant topic. Around the same time, in the mid-2000s, a group of researchers from Temple University, led by Charles Fisher, conducted a series of dives into the scallop lakes of the Gulf of Mexico to study the ecosystems along their periphery. It was during this time that colonies of the genus Bathymodiolus, giant deep-sea mussels living in symbiosis with chemosynthetic bacteria, were described in detail. These mussels can reach lengths of 20 centimeters and form dense colonies right at the boundary of the brine, where hydrogen sulfide concentration is maximized for life and minimized for death. This is a delicate balance that they found through trial, error, and millions of years of evolution. Humans do not have the time for such work. There is another aspect in the scallop lakes of the Gulf of Mexico that goes beyond pure biology and enters an area that can be loosely described as the geopolitics of the seabed. The brine, saturated with magnesium chloride and other compounds, is an indicator of oil and gas deposits. Where there are salt diapirs and scallop lakes, there are usually hydrocarbons as well. The Gulf of Mexico is one of the largest oil and gas-bearing regions in the world, and the scallop lakes literally serve as markers for reservoirs. Oil companies fund part of the scientific expeditions to these anomalies, not out of altruism, but because they understand that where nature has placed a grim and beautiful sign saying, "There's something here," there usually is something indeed. This adds an additional dimension to the scallop lakes. They are simultaneously an ecosystem, a geological phenomenon, and an economic asset. The abyss is multifunctional. The disaster on the Deepwater Horizon platform in 2010, the largest oil catastrophe in the history of American shipping, occurred precisely in the Gulf of Mexico, rich with such geological anomalies, although the immediate cause of the disaster was not directly related to the scallop lakes. Nevertheless, studies conducted after the disaster revealed that the oil that settled on the seabed altered the chemical composition of the water near several scallop lakes. Specifically, it disrupted the oxygen regime at the bottom layer. Bacterial mats along the shores of certain lakes have died off or significantly diminished. The recovery continues to this day. A person once briefly touched this place, and it is still healing from that touch. The Gulf of Mexico's brine lakes serve as a reminder that the planet is arranged in a much more complex way than it appears from the view of an airplane or even from the deck of a research vessel. There, 800 meters beneath the water's surface, exist entities that challenge our basic intuitions about what water should look like, where life should be, and what we should consider dangerous. The brine lake does not appear to be a threat. It looks like a wonder. It is the most sophisticated form of danger, the kind that masquerades as beauty. Do not dive into water that looks like a mirror, especially if that mirror is at the bottom of another body of water. The next depth does not kill with brine or boil with hot water. It kills with darkness, pressure, and what dwells in that darkness, creatures about which you know exactly as much as nature deemed necessary to inform you, which is almost nothing. We are heading into the bathypelagic zone, the midwater where the last traces of sunlight vanish and a world conceived without the participation of daylight begins. Depth 4, bathypelagic, the midwater abyss where light dies completely. There is a precise, measurable, documented moment during a dive when the last photon of sunlight disappears. It does not fade gradually or dissolve into twilight. It simply disappears. Just a second ago, the blueness around was barely visible, and now it's gone. Completely. This occurs at a depth of about 1,000 meters, and oceanographers refer to this boundary as the lower limit of the mesopelagic zone, the twilight zone. Below this begins the bathypelagic, a layer of water from 1,000 to 4,000 meters deep, occupying more volume than any other habitat on Earth. This is not the ocean floor. It is not even close to the bottom. It is just open water, a body where there is no top or bottom in human understanding, nor surface nor ground. Only pressure, cold, and darkness stretch for thousands of kilometers in every direction. The bathypelagic occupies about 60% of the total volume of Earth's biosphere. It is the largest ecosystem on the planet by volume, and one of the least studied. Humans have explored less than 5% of this zone. For comparison, the surface of the Moon has been fully mapped, and the surface of Mars is nearly fully mapped. The bathypelagic. No, this is not a metaphor about human ignorance. It is a literal fact. We live on a planet where 95% of the largest habitat has never been seen by us. The temperature in the bathypelagic remains between 1 and 4 degrees Celsius throughout the layer, with minor local variations near underwater ridges and volcanic structures. This is not cool or cold in a casual sense. This is the temperature at which the human body loses the ability to maintain normal metabolism in about 20 to 30 minutes without a wetsuit. Even if the pressure allowed for the existence of an unprotected person at this depth, and it does not, ranging from 100 to 400 atmospheres depending on the specific marker, the cold would finish what it started before you even realized where you were. The body loses heat in water about 25 times faster than in air. The bathypelagic zone does not leave time for contemplation. The pressure in this zone increases linearly. Every 10 meters of depth adds 1 atmosphere. At 1,000 meters, there are 100 atmospheres. At 2,000 meters, there are 200. At 4,000 meters, at the lower boundary of the bathypelagic zone, there are 400. 400 atmospheres means that every square centimeter of your body's surface would experience a load equivalent to 40 kilograms. The human body contains cavities, lungs, nasal sinuses, middle ear, intestines. These cavities are filled with gas or air. When pressure increases suddenly, gas compresses. This is Boyle's law, known to every school student who has taken physics. The lungs collapse. Eardrums rupture. Blood becomes saturated with nitrogen to critical levels, and upon returning to the surface, if it ever happens, that nitrogen comes out of solution as bubbles right in the bloodstream and tissues. This is called decompression sickness, and in severe cases, it kills as reliably as the pressure of depth itself. But pressure and cold are just physics. The bathypelagic zone is interesting not only for its physics, it is compelling because of what lives within it. The list of creatures in the bathypelagic zone sounds like the inventory of props for a horror movie directed by a biologist with an unhealthy imagination. Let's start with the relatively harmless. Squid of the genus Vampiroteuthis infernalis, literally hellish vampire squid, inhabit the bathypelagic zone at depths ranging from 600 to 1,200 meters. They are neither squids nor octopuses in the strict sense. They belong to a separate order of cephalopods, unique in their kind, representing an intermediate evolutionary form between the two groups. The hellish vampire has red eyes, the largest relative to body size among all animals on the planet. Each eye measures approximately 9 centimeters in diameter with a body length of around 30 centimeters. This ratio means that the creature sees better in the dark than any other animal on Earth, although seeing in the dark, where not a single photon exists, is a conditional concept. It detects bioluminescent flashes, the only source of information in the absolute darkness of the bathypelagic zone. Bioluminescence deserves a separate discussion because in the bathypelagic zone, it is not a decorative addition but the primary means of communication, hunting, and protection. Various estimates suggest that from 70 to 90% of all organisms in the bathypelagic zone are capable of generating light. This is not a rarity or an exception, it is the norm. The mechanisms of luminescence in different organisms vary fundamentally. Some use a chemical reaction of luciferin oxidation with the help of the enzyme luciferase, while others contain symbiotic light-emitting bacteria in specialized organs, photophores. The anglerfish, a member of the Lophiiformes order, uses a bioluminescent fishing pole above its head to attract prey. This image is so well known, thanks to the animated film Finding Nemo, that many people think, since it's in a cartoon, it must be something adorable. In reality, female anglerfish can reach a length of 60 centimeters, and their inward-angled teeth prevent prey from escaping. Their mouths can open so wide that they can swallow prey larger than themselves. This is what evolution looks like under an absolute scarcity of resources. The giant squid, Architeuthis dux, primarily inhabits the mesopelagic and upper bathypelagic zones. Its tentacles can reach lengths of 18 meters. Its eyes are the largest of any creature that has ever lived on Earth, measuring up to 30 centimeters in diameter. The first photograph of a live giant squid in its natural habitat was only captured in 2004 by Japanese scientists Tsunemi Kubodera and Kyoichi Mori. Until that moment, everything scientists knew about the giant squid came from the stomachs of sperm whales and dead bodies washed ashore. Notably, the photographing happened by chance. The researchers lowered a camera with an automatic shutter release to a depth of around 900 meters near the Bonin Islands. The camera captured the moment when the squid attacked the bait. A part of its tentacle was left behind, torn off during the squid's attempt to escape. This piece was approximately 5.5 meters long, a small part of a tentacle. In 2012, a Japanese television team from NHK, together with researchers from the Japan Agency for Marine Earth Science and Technology, conducted the first successful video recording of a live giant squid at a depth of around 900 meters. They used a specially designed camera with red light, presumably invisible to the squid, and bait in the form of a small imitator of bioluminescent plankton. The squid suddenly emerged from the darkness and attacked the bait with such speed that the operator monitoring the screen later described it as an explosion from nothing. The creature on the video looked exactly how something that has never seen sunlight should look: silvery golden with enormous pupils, moving with a grace that is both beautiful and deeply unsettling for the observer. The colossal squid, Masonicotuthis hamiltoni, is larger than the giant squid and dwells at greater depths. Its maximum recorded length is about 14 meters, but scientists believe there are specimens that are significantly larger based on the traces of suckers found on sperm whale skin. The suckers of the colossal squid are equipped with hooks, rotating sharp claws at the edge of each sucker. The marks left by these hooks on sperm whale skin sometimes reach the size of a dinner plate, corresponding to suckers measuring several dozen centimeters in diameter. What size should a tentacle with such a suction cup be? And what about a body with such a tentacle? The mathematics of this calculation conjures images that Lovecraft would describe with delight, while any other person might prefer not to think too deeply about it. Research on the bathypelagic zone in the 20th century was accompanied by a series of episodes that are difficult to classify definitively. In 1960, an American atomic submarine, the Thresher, more accurately its predecessor of the same type, detected a series of acoustic signals in the Atlantic Ocean that the operators could not immediately identify. The signals did not correspond to any known type of biological noise or any known type of mechanical noise. Later analysis suggested that it could have been the singing of sperm whales at a specific frequency, combined with reverberation from the underwater terrain. It could have been, indeed, that's the case. A precise answer was never provided. In 1997, the hydrophone network of the National Oceanic and Atmospheric Administration recorded a sound that was named bloop. This was one of the loudest sounds ever recorded in the ocean. Its power allowed it to be detected from a distance of about 5,000 kilometers from the source. The shape of the signal resembled biological noise, that is, a sound produced by a living creature. The problem was that the source of the sound, based on its parameters, had to be significantly larger than a blue whale, the largest creature to have ever lived on Earth. The internet immediately proclaimed the bloop as proof of the existence of Cthulhu, and this interpretation spread far wider than the official explanation published in 2012. Scientists determined that the sound was generated by a breaking Antarctic iceberg. Notably, the explanation is scientifically correct, but it does not diminish the fact that an iceberg producing such a sound must have been colossal, comparable in size to a small country. The bathypelagic zone is an area where our understanding of life meets conditions under which life seems impossible. And yet, it exists there. Every year, scientists describe new species discovered in the bathypelagic zone, numbering in the dozens each year. Each expedition with remotely operated vehicles returns with footage of creatures no one has ever seen before. This is not an exaggeration or romanticization. In 2023, one expedition by the Ocean Research Institute in the Galapagos Islands documented over 100 new species of deep-sea organisms in just 2 weeks. 100 new species in 2 weeks, in one location. There is something simultaneously inspiring and unsettling about the realization that on your planet, in an environment that occupies a significant portion of its biosphere, something new is discovered every week that you didn't know before. This means that the world is significantly larger than your map. This also means that it is home to creatures that have never known of your existence, and they do just fine without that knowledge. Leave the bathypelagic zone alone. Not because it is aggressive, because it is vast, dark, and completely self-sufficient. and you are no more than a random guest within it, lacking necessary pressure in your tissues, bioluminescent bait, or hooks with suckers. The next depth is of an entirely different nature. We leave the open water and descend to the bottom, not to a calm sedimentary cover, and not to basalt fields. We head toward a volcano, an underwater volcano that does not sleep, does not remain silent, and has no intention of pretending that your presence does not concern it. Welcome to the Howe Basin caldera, where the ocean floor once decided to become the sky. Depth 5. Howe Basin caldera, the volcano that breathes from below. There is a special category of places that are dangerous not because they do something to you, but because they do something to the space around you. The Challenger Deep presses down. Hydrothermal vents boil. Cone snail lakes dissolve. The bathypelagic zone swallows in darkness. The Howe Basin caldera, an underwater volcanic complex in the southwestern Pacific Ocean, northeast of Tonga, does something fundamentally different. It rewrites the very seafloor beneath your feet, literally. Right now, as you read this, the floor of the caldera is rising, sinking, cracking, and rising again. This is not a metaphor for geological activity. This is a description of what happens there every few years, with an amplitude of tens of meters. Howe Basin is not a single volcano. It is a system of volcanic structures, calderas, and rift fissures located at depths of 500 to 1,800 meters. The central caldera, the Howe Pool, is a depression about 8 kilometers in diameter, formed by the collapse of the roof of a magma chamber after a major eruption. This is a classic caldera structure, the same geology as Yellowstone or Vesuvius, only flipped. Not a mountain with a hole on top, but a hole at the bottom of the ocean with a mountain inside. Inside the caldera is the cone of a new volcano, the Howe Cone, which has grown over the past few decades to a height of about 100 meters from the floor of the caldera. It is growing, slowly but continuously. What attracts researchers here, aside from the obvious scientific interest in active underwater volcanism, is that Howe Basin is one of the few places on the planet where one can observe the formation of new oceanic crust in near real time. Each eruption adds a layer of basalt to the caldera floor. Each layer is a page of geological history being written right now. It is like watching a book being written, only the book is written with fire and stone, and each page weighs several million tons. The first detailed study of the Howe Basin caldera was conducted in 1984 by an American-French expedition aboard the research vessel Thomas Washington. At that time, scientists recorded intense hydrothermal activity around the perimeter of the caldera, along with fresh lava flows on the seafloor, evidence of a recent eruption in geological terms. By recent, geologists mean within the last few thousand years, which sounds unconvincingly reassuring to an underwater researcher. The next significant surge of activity was documented in 1991. Seismographs throughout the Pacific region registered a series of earthquakes with magnitudes ranging from 4 to 5.5, centered in the Howe Basin area. A research expedition sent to this region about 6 weeks after the seismic events discovered that the seafloor had changed. Where specific lava formations had been documented in the previous survey, fresh basalt was now present. Old hydrothermal vents had disappeared, and new ones had emerged. The inner cone had grown by approximately 7 meters. All of this occurred in just 6 weeks, while the expedition was making its way to the site. The seafloor is not stable in the human sense of a constant foundation. It is a surface that reconsiders. It is essential to pause and consider what happens during an underwater eruption in a caldera complex of this type, because the physics of the process differs significantly from that of a terrestrial eruption, and these differences mainly tend toward even more dangerous. On the surface, a volcanic eruption is accompanied by lava flows, ash emissions, pyroclastic flows, and lava bombs. All of this is deadly but at least predictable in direction, down the slope. Underwater, everything is different. Superheated magma, when it comes into contact with seawater, causes instantaneous explosive vaporization, a phreatomagmatic explosion. The water around the vent boils instantly, creating a pressure shock wave that propagates in all directions at a speed of around 1,500 meters per second, approximately 4 times faster than the speed of sound in air. For any object within a few hundred meters of the explosion's source, this means exposure to pressures incompatible with structural integrity. The hull of a research vessel, designed for static water pressure, is not built to withstand the dynamic pressure of an explosion. These are different physical stresses, and engineers who design submersibles are aware of this, although they prefer not to emphasize it to the public. In addition to the shock wave, an underwater eruption produces several additional destructive factors. Lava pillows, a distinctive form of underwater lava that forms from rapid cooling, roll down the slopes of the caldera at speeds sufficient to bury any object in their path under several tons of basalt. Gas bubbles, primarily carbon dioxide and sulfur dioxide, are released from the magma and rise to the surface, creating zones of decreased water density. A vessel positioned above such a zone loses buoyancy as the water beneath it becomes too saturated with gas to support the hull. This phenomenon has been documented in several cases, although the vessels themselves generally manage to leave the danger zone. Generally is precisely the caveat that one wants to remove from the sentence, but it cannot be. In 2009, the research vessel Thomas G. Thompson from the University of Washington conducted detailed mapping of the caldera using multi-beam sonar and a series of dives by the remotely operated vehicle, ROPOS. The results of the survey indicated that between 1998 and 2009, the floor of the caldera in the central part rose by approximately 75 meters. 75 meters is the height of a 25-story building. In 11 years, the floor of the caldera grew to the height of a skyscraper. No one saw this. There were no observers. One day, the next expedition arrived and discovered that the maps were outdated. The ROPOS, during one of its dives in 2009, approached the active vent at the edge of the inner cone and recorded something that the operators initially mistook for noise on the screen. It was a molten sulfur lake, a lake of liquid sulfur, stably existing at a temperature of around 130 degrees Celsius at the pressure of that depth. Yellow, viscous, with characteristic bubbling surface movements. It was real. Liquid sulfur, stable at normal atmospheric pressure only above 120 degrees, existed here as a permanent body of water. Surrounding the lake, colonies of thermophilic microorganisms were recorded. The researchers observed in silence for several minutes before one of them spoke into the microphone words that were later quoted in the official report of the expedition. The words were unprintable. The liquid sulfur lake at the bottom of an underwater volcano is something that the game Subnautica would recreate as a backdrop for a final boss. The difference is that there is no final boss here. There is only a place that looks like a final boss, constantly, regardless of whether you are looking at it or not. The Hawaii Basin ecosystem, for all its aggressiveness, is one of the richest deep-sea ecosystems in the Pacific Ocean. Active hydrothermal activity provides a constant influx of chemical energy, a substrate for chemosynthetic bacteria that serve as the foundation of the food chain. Here, clusters of tube worms of the genus Riftia pachyptilla have been recorded, those first described at the Galapagos Rift in 1977. Specific types of crabs live right near vents with temperatures above 100 degrees, behavior that is difficult to explain in terms of normal thermal balance, yet it has been documented on video. Bacteria that are resistant to concentrations of sulfuric acid, deadly for most known forms of life, have been found here. Every time scientists think they have discovered the limits of biological tolerance to extreme conditions, something alive in the Hawaii Basin pushes that limit even further. There is an aspect of the history of Hawaii Basin that remains largely unknown beyond a narrow circle of volcanologists and geologists. In 1998, a few months before a significant seismic event in the area, the NOAA hydrophone network recorded an acoustic anomaly known internally as the T-wave burst, a series of powerful T-wave type acoustic impulses characteristic of volcanic events. These signals were detected by stations up to 3,000 kilometers away, which corresponds to an extremely high energy source. This preceded the eruption by about 8 weeks, enough time for any observers in the caldera to have made their escape. There were no observers. That's fortunate. The Howe Basin teaches a lesson that is often the most difficult for researchers to grasp. Some places do not remain as you found them. You have mapped the seafloor. It has shifted. You studied the vent. It has disappeared. You recorded the temperature. It has doubled. The world underwater is under no obligation to stay unchanged for your convenience. It is busy with its own affairs, ancient, vast, and completely indifferent to your presence. When a geologist says he studies a living planet, he means just that, not a metaphor. The literal movement, breathing, and growth of the planetary crust, right now, right beneath you. Leave Howe Basin alone. The seafloor there is unstable, the temperature is unpredictable, and the liquid sulfur in the lake shines a yellow hue that could appear beautiful under different circumstances. The next depth lies significantly farther north and is fundamentally colder. There, sulfur does not boil, and basalt does not crack. There is a darkness of another kind, not absolute, but grayish, cloudy, permeated by suspended particles carried by the Arctic water from beneath the ice. This is where the Arctic Ocean reveals its true face, not the romantic polar side, but what it becomes at depth, in darkness, beneath the ice, when the surface is far away and the way up is obstructed. Depth 6. Nansen Basin, the Arctic Abyss. Beneath the ice. There is a cold that you know. It is the cold of a winter morning, when your breath turns to vapor and your fingers go numb in gloves. There is a cold you can imagine, -40 in the Siberian taiga, the wind from the icy plains, the darkness of the polar night. And then there is the cold of Nansen Basin, and this is not a temperature that the human imagination reproduces accurately, because here, cold is not just a climatic characteristic, but a structural element of the universe. Nansen Basin is located in the Arctic Ocean, north of the Spitsbergen Archipelago and Franz Josef Land, and it is one of the deepest basins in the Arctic Basin. Its maximum depth reaches about 3,850 meters. Above it lies an ice shield, permanent, perennial, with a thickness ranging from 1.5 to 4 meters, and in some places up to 10. This is not just a roof over the abyss, it is a locked door that you cannot open from the inside. The depression is named after Fridtjof Nansen, a Norwegian explorer, oceanographer, and diplomat who in 1993 intentionally froze his ship, the Fram, in Arctic ice and allowed it to drift through the Arctic Ocean for 3 years. This was one of the most radical scientific experiments in the history of polar research. Nansen calculated that the drift of the ice would carry the ship through subpolar areas if he simply allowed it to move with the ice. His calculation proved correct. The Fram traversed the Arctic Basin and was freed from the ice off the coast of Spitsbergen. During this drift, Nansen took systematic measurements of depths, temperatures, and salinity, the first detailed data on the oceanography of the Central Arctic. What he measured from aboard a wooden sailing ship frozen in ice at the end of the 19th century continues to be part of the fundamental datasets of Arctic oceanography today. Nansen discovered something paradoxical. At depths of several hundred meters in Arctic waters, the temperature of the water did not decrease, but rather increased, relative to the surface layer. This phenomenon, later termed the Atlantic layer, can be explained by the influx of warm Atlantic waters, which enter the Arctic Ocean through the Fram Strait between Spitsbergen and Greenland and sink to intermediate depths, from 200 to 900 meters. These waters are 1 to 2 degrees warmer than the surrounding Arctic waters, which is a significant difference in the context of the polar ocean. They carry with them not only warmth, but also salt, and it is their presence that forms the characteristic layered structure of Arctic waters, where layers of different temperatures and salinities do not mix, creating something akin to a layered cake with a very cold filling. The surface layer of water in the Nansen Basin, under the ice cover, has a temperature of about -1.8 degrees Celsius. This is below zero, but the water does not freeze. The salinity of Arctic water lowers the freezing point to around -2 degrees. In other words, this water exists in a state where it is simultaneously a liquid and striving to become ice, balancing on this edge constantly for millions of years. This thermodynamic equilibrium at the edge of a phase transition is a state that physicists find elegant, while a diver without a wetsuit would find fatal in about 3 minutes. Under the ice of the Nansen Basin, it is dark. Not as dark as in the bathypelagic zone. The ice lets in some scattered light during the polar day, creating a faint bluish glow in the upper few meters of water. But below about 50 meters, the light disappears completely, and darkness begins, lasting all the way to the bottom, nearly 3,800 meters down. This darkness is not just visual, it is climatic, ecological, and historical darkness. The Arctic Ocean has been closed off by ice for millions of years. The ecosystems that have developed here evolved under conditions where sunlight is an exception rather than the rule. Life beneath the ice of the Arctic is organized differently than in any other marine ecosystem. The underside of the ice is not a blank boundary, but a substrate. It is home to algae, primarily diatoms and the ice algae of the genus Melocera arctica, which hang down from the underside of the ice in long strands, sometimes reaching several meters. During polar summer, these algae produce up to half of all primary biological production in the Arctic basin. This is a phenomenal concentration of life in conditions that should exclude it. The algae are eaten by copepods, tiny crustaceans, mere millimeters in size, numbering literally in the trillions in Arctic waters. Arctic cod and capelin eat the copepods. Narwhals, belugas, Greenland seals, and ringed seals eat the cod and capelin. Seals are preyed upon by polar bears. This forms a pyramid whose foundation rests on algae just a few micrometers thick, living on the underside of the ice in almost total darkness at temperatures close to freezing. The Nansen Basin is where the most desperate polar explorers in history encountered the ocean. After Nansen, many turned to the Arctic Basin, and not all returned as he did. In 1926, the Italian airship Norway, commanded by Umberto Nobile, crossed the Arctic Basin from Spitsbergen to Alaska, the first confirmed flight over the North Pole. 2 years later, Nobile undertook a second expedition on the airship Italia. The airship crashed over the Arctic ice. Part of the crew, 16 men, found themselves on a drifting ice floe above the Nansen Basin. They spent 49 days there before being rescued by the Soviet icebreaker Krasen. Roald Amundsen, the first person to reach the South Pole, set out to find Nobile by plane and disappeared over the Barents Sea. His body was never found. This is not an underwater story, but it is a tale of the Arctic, which takes people not only from below, but also from above. During the Cold War, the Nansen Basin and the Arctic Basin as a whole became a battleground for the Soviet and American nuclear submarines. Beneath the ice of the Arctic Ocean, vessels from both sides maintained combat readiness, hiding from the enemy's hydrophones and thermoclines, using the acoustic properties of the layered Arctic waters to mask their presence. The Nansen Basin was of particular interest in this regard. Its depth was sufficient for submarine maneuvering, and its proximity to Soviet bases on the Kola Peninsula made it strategically significant. In 1968, the American nuclear submarine Scorpion sank in the Atlantic under unexplained circumstances with a crew of 99 men. The official explanation is a torpedo malfunction or mechanical failure. Soviet sources from that period spoke of something else. Documents related to this case are partially declassified, partially not. The Arctic can keep secrets as reliably as it keeps the cold. In 1985, the Soviet nuclear submarine K-278 Komsomolets, a fundamentally new project, the only submarine made of titanium alloy capable of diving to depths greater than 1,000 meters, was tested in the Norwegian Sea, bordering the Nansen Basin. The trials were successful. The submarine set a record diving depth for combat submarines, reaching 1,027 meters. 4 years later, in 1989, the Komsomolet sank in the same area, the Norwegian Sea, at a depth of around 1,680 meters due to a fire on board. Out of a crew of 69, 42 lost their lives. The submarine lies there still, on the seabed, with 2 nuclear torpedoes on board. Periodically, Norwegian scientists monitor the radioactive background in this area. The data is published. It does not cause panic. However, it does not bring comfort either. Contemporary research in the Nansen Basin is focused on what is happening to it in the context of climate change. The Arctic is warming approximately 4 times faster than the rest of the planet. The area of summer sea ice in the Arctic Ocean has shrunk by around 40% over the last 40 years. The Nansen Basin is one of the areas where seasonal ice melting has become significantly more pronounced than before. This is not just an environmental issue, it is geopolitical as well. The opening of Arctic waters means access to rumored oil and gas deposits, to new shipping routes, the Northern Sea Route, and to fishing areas previously blocked by ice. Russia, Norway, Denmark, Canada, and the United States have been engaged in diplomatic and legal discussions about the delineation of the Arctic shelf for several decades. The Nansen Basin is in a zone that several countries claim as their own. This is one of the rare cases where the abyss is a subject of litigation. A research expedition by the Norwegian Polar Institute aboard the vessel Lance in 2014 spent several months in the Nansen Basin, drifting alongside the ice, intentionally replicating the method used by Nansen 120 years ago. Scientists studied changes in the structure of the ice cover, the chemical composition of the water, and the condition of under-ice ecosystems. One of the expedition participants, Norwegian biologist Paul Drinen, described the moment he first lowered a camera under the ice in the basin area. You see the underside of the ice, uneven, bumpy, bluish, and it extends into the darkness in all directions to the horizon. You are below the roof of the world. This is not the poetry of a researcher. It is an accurate description of the geometry of the place. The Nansen Basin is not a place that kills dramatically. It kills methodically, patiently, and without unnecessary effects. The cold here does not attack. It simply exists. The ice above does not crush down. It merely blocks the path above. The darkness does not consume. It simply exists, and it was here long before you, and it will remain after you. This is the Arctic version of nature's indifference, the very one we discussed in relation to bathypelagic zones, only here it is white, flat, and very quiet. Leave Nansen Basin alone. Not because there is nothing interesting there. Everything is interesting. It's just that what is interesting exists under conditions that are incompatible with your survival. This is a small but fundamental obstacle. Now we move from the cold to the warmth, but this warmth is neither that of the Mediterranean nor a tropical beach. This warmth is hidden, buried, rising from below. We are heading where the Mediterranean Sea conceals something at its bottom, something that most people floating on its surface in yachts and ferries have no idea about. The next depth is Lake Kilo, a hypersaline basin at the bottom of the Mediterranean Sea that knows how to wait. Depth 7. Lake Kilo and the pools of the Mediterranean abyss, the salt that remembers everything. The Mediterranean Sea is a deception, not malicious and not intentional, but systemic and completely consistent. From the surface, it looks exactly as a sea around which 3,000 years of civilization have grown. Blue, warm, clear near the shore, sparkling in the sun, smelling of salt and rosemary. The Phoenicians, Greeks, Romans, Arabs, Venetians, all of them looked at this water and thought they understood it. All were equally mistaken. Beneath the surface of the Mediterranean Sea, at depths ranging from 3,000 to 5,000 meters, lie objects of which humanity had no inkling until the end of the 20th century. These objects rewrite the history of the sea itself, not its cultural history, but its geological history, and do so with such serene thoroughness that you want to sit down and rethink everything you thought about the Mediterranean. About 5,900,000 years ago, the Mediterranean Sea dried up, completely. This is known as the Messinian salinity crisis, and it is one of the most dramatic geological events in the planet's history over the last few tens of millions of years. Tectonic movement closed the Strait of Gibraltar, which did not yet exist in its modern form, and the Mediterranean Sea, deprived of its Atlantic water inflow, began to evaporate. Evaporation in Mediterranean climate conditions significantly exceeds precipitation. The sea became shallower. It became shallower still. Finally, it dried up entirely, leaving behind a vast basin up to 5 kilometers below sea level, covered with a thick layer of salt and evaporites, sedimentary rocks formed by evaporated water. This layer of salt reaches up to 3 kilometers in thickness in places. This is more than the height of many alpine peaks. All this salt was the sea. About 600,000 years later, in Messinian terms, this is quick, the Atlantic broke through Gibraltar. It was not a gradual filling, but a catastrophic flow. Geologists estimate that the level of the Mediterranean Sea rose by several meters per day for many years. The waterfall in the Strait of Gibraltar was thousands of times more powerful than Niagara Falls, the largest waterfall in the planet's history over the past few million years. The basin is filled up, the sea has returned, but the salt at the bottom remains. And it is precisely this salt, which is 5,900,000 years old, that creates the objects at the bottom of the Mediterranean Sea that we came to study. Under the pressure of kilometers of water and sediment, the salt layers begin to flow, slowly, but in geological terms, quickly. Where the roof of the salt layer breaks through, brine rises to the seafloor and collects in the depressions of the landscape, forming hypersaline pools, just like those in the Gulf of Mexico, but significantly older, much larger, and with a history dating back to an era when the Mediterranean Sea did not exist in its current form. Lake Kilo, officially known as the l'Atalante Basin, but often referred to in scientific literature by the name of the research vessel that first described it in detail, is located at the bottom of the Ionian Sea, south of the Greek coast, at a depth of about 3,500 meters. It is one of the largest hypersaline basins in the Mediterranean, about 8 kilometers long, around 2.5 kilometers wide, and approximately 300 meters deep. The brine here is so saturated that its density is nearly double that of regular seawater. This is not very salty water. This is a liquid with fundamentally different physical properties, separated from the surrounding ocean by a distinct halocline, a layer of sharp density transition, just as oil separates from water in a glass. The first detailed study of the l'Atalante Basin was conducted in 1993 by the French research vessel Atlante, after which it received its unofficial name. Scientists lowered a remotely operated vehicle to the surface of the brine and captured images that their colleagues initially refused to accept as real. A perfectly flat, mirror-like surface at a depth of 3,500 meters, reflecting the light from the vehicle's spotlights like polished metal, with a clear shoreline and, that was unexpected, visible waves crashing against that shore. The waves were created by the movement of water in the bottom layer above the brine. It was a lake, a real one, with waves, with shores, with a mirror-like surface, at the bottom of another sea at a depth of 3,500 meters. The brine in the l'Atalante Basin is virtually devoid of oxygen. This is an anoxic environment, the kind in which most known forms of life cannot exist. Almost cannot. In 2010, a group of scientists led by Roberto da Navarro from the Polytechnic University of Marche published an article in the journal BMC Biology that immediately attracted the attention of the world's scientific media. Live multicellular organisms, loricifers, tiny invertebrates about 1 millimeter in size, were discovered in brine samples from the l'Atalante Basin. This became the first documented case of multicellular animals found in a completely anoxic environment. Until that moment, it was believed that multicellular life without oxygen was impossible. The Lorio Atalante not only existed without oxygen, but they also reproduced, formed eggs, and lived a complete life cycle. Their mitochondria, cell organelles responsible for aerobic respiration in most living beings, evolved into something fundamentally different. Instead of oxygen, they use other oxidizers. Evolution, as always, found a way. This discovery sparked a discussion in the scientific community that continues to this day. Some researchers question the interpretation of the data, suggesting that the organisms might have been dead and simply well preserved in brine. However, da Navarro's team insists that biochemical markers of metabolic activity were present. The controversy is methodological, but the stakes are enormous. If multicellular life can exist without oxygen, it completely rewrites our understanding of the possible conditions for life, including on other planets. The Discovery Basin is another hypersaline location in the Mediterranean, situated in the eastern part of the sea, southwest of Crete, at a depth of about 3,300 meters. It was discovered in 1993 by the British research vessel Discovery, hence the name. The Discovery Basin is significantly larger than l'Atalante, measuring around 30 kilometers in length and about 10 in width. Its brine is saturated with magnesium chloride to such an extent that the water's pH is around 5, indicating a mildly acidic environment that is aggressive to most biological molecules. The concentration of hydrogen sulfide here is also high. Considering these factors, the Discovery Basin is one of the most toxic aquatic locations in the Mediterranean, and at the same time, one of the most studied due to its relatively easy access compared to locations in the Pacific Ocean. Research in the Discovery Basin during the 2000s revealed an interesting pattern. Along the basin's perimeter, at the boundary of brine and normal seawater, there exist dense bacterial mats, exactly like those found at the edges of the Rapa-Welk lakes in the Gulf of Mexico. These mats are formed by several species of sulfate-reducing bacteria that use sulfates from the brine as a terminal electron acceptor in the process of anaerobic respiration. In simpler terms, these bacteria breathe sulfate instead of oxygen and produce hydrogen sulfide as a byproduct of their metabolism. This hydrogen sulfide makes the water even more toxic. It creates a closed cycle of self-poisoning, in which the bacteria are both the producers of the toxin and its consumers, an ecosystem built on its own toxin. The Theo Basin, the third major hypersaline object in the eastern Mediterranean, is located northeast of the Discovery Basin, at a depth of about 3,400 meters. Its uniqueness lies in the fact that the brines feeding it rise from several different salt layers of varying geological ages, resulting in differing chemical compositions of the water in different parts of the basin. This makes it scientifically valuable. It allows for the comparison of ecosystems existing under different chemical conditions within a single water body. It also makes navigation unpredictable. The boundaries of chemical zones are not visually apparent, and an apparatus moving along the bottom of a basin can unexpectedly find itself in an environment with completely different chemical characteristics than the operators anticipated. In 2006, a French expedition aboard the vessel Rosenson was mapping the seafloor of the eastern Mediterranean in the Tyrrhenian Sea Basin. During one of the remotely operated vehicle dives, the operators recorded an anomaly. A sonar screen showed an object on the seabed that did not match any known geological structures. The object was relatively small, about 20 meters long, and had a regular rectangular shape. As the apparatus approached, it became clear that it was the hull of a ship, an ancient ship. The amphoras scattered around indicated an antiquity period. It lay directly on the edge of the salt basin, partially buried in sediment. The Mediterranean seabed holds thousands of such finds. Trade routes existed here for 3,000 years, and some ships never reached their destination. The brine of the basin, due to its chemical aggressiveness to biological material, destroyed organic remains, wood, fabrics, everything organic. However, metallic objects, anchors, clamps, tools, and ceramics have remained almost perfectly intact. The brine both kills and preserves at the same time. This is yet another of its dualities. The history of exploring the Mediterranean Sea is a story of misunderstanding its depths. The Phoenicians knew its winds and currents. The Greeks created its first maps. The Romans called it Mare Nostrum, our sea. Arab geographers described its shores with astonishing accuracy, yet none of them knew that this sea has a bottom that remembers a time when the sea itself did not exist. That beneath layers of water and sediment lies the salt of an epoch predating human history by several million years. That in the basins of this salt live creatures that defy fundamental biological rules. Mare Nostrum, our sea, turned out to be significantly less ours than those who named it believed. Leave the basins of the Mediterranean abyss undisturbed. Not because they are uninteresting, they are more fascinating than most places on Earth. Rather, they exist by rules written over 5 million years of geological history, not by the safety agreements for dives that people created. We move further on, this time permanently leaving familiar latitudes behind. The next depth is where the Indian Ocean meets a tectonic boundary capable of reshaping the planet. It's the location of an event in 2004 that killed 220,000 people, not at depth but on the surface, where the depths reached out with their long arm. We are heading to the subduction zone of the Sunda Trench. Depth 8. The Sunda Trench, the abyss that kills on the surface. There are depths that kill you as you descend to them, and there are depths that kill you when you stand on the shore 300 kilometers away and look at the horizon. The Sunda Trench is classified as a second category. This is not a metaphor, nor an exaggeration. On December 26, 2004, at 8:58 local time, an earthquake with a magnitude of 9.1 struck about 30 kilometers beneath the seabed of the Sunda Trench, one of the most powerful quakes in the history of instrumental observation, and the third strongest earthquake recorded since the invention of the seismograph. The rupture of tectonic plates stretched approximately 1,200 kilometers along the subduction zone. The ocean floor in the area of the epicenter rose several meters in just a few minutes. These several meters of seabed, multiplied by the area of the rupture spanning thousands of square kilometers, displaced a volume of water comparable to several cubic kilometers. The wave spread in all directions at a speed of around 800 kilometers per hour, a jet plane speed. 220,000 people in 14 countries lost their lives. This was the tsunami of the Indian Ocean in 2004, and it began here, in the Sunda Trench, at a depth that most of its victims had never seen in their lives. The Sunda Trench, or Java Trench as it is sometimes called after the nearest large island, extends approximately 5,000 kilometers along the southern and western coast of the Indonesian archipelago. Its maximum depth is about 7,250 meters. This is the Sunda Basin, less known than the Mariana, but incomparably more dangerous for humanity due to its lethal tectonic activity. This is where the Australian lithospheric plate is subducting beneath the Sunda Plate at a rate of about 6 to 7 centimeters per year, which is quite significant in geological terms. This subduction process has created the Java-Sumatra volcanic arc, a chain of volcanoes stretching along Sumatra and Java. It is here that Krakatoa is located, a volcano whose eruption in 1883 was heard in Australia and triggered a tsunami that killed around 36,000 people. This proximity, the subduction trench and the volcanic arc, creates a geological environment where tectonic catastrophes are not exceptions. They are the norm, occurring every few hundred years. To understand why the Sunda Trench kills the way it does, indirectly, not through pressure or cold, but remotely through waves, you need to grasp the mechanism of subduction in this particular place. The Australian plate, sinking beneath the Sunda Plate, drags along the upper layer of the crust, the very one on which the ocean floor rests. In areas of maximum stress, where friction between the plates accumulates over centuries, this layer bends, deforms, and at some point slips, releasing the accumulated energy instantly. This phenomenon is called a megathrust earthquake, an earthquake in a subduction zone, and such earthquakes produce the most devastating tsunamis because they displace not just a localized point, but a vast area of the ocean floor. The mechanism of a tsunami is fundamentally different from what most people imagine. In the open ocean, a tsunami is not a giant wave. It is a barely noticeable bulge in the surface, about half a meter to 1 meter high, stretched over hundreds of kilometers in length. A ship in the open sea wouldn't feel it at all, just a slow and gentle rise and fall. The speed of a tsunami in deep ocean is determined by a simple formula. It is equal to the square root of the product of gravitational acceleration and depth. At a depth of 4,000 meters, which is the average depth of the Indian Ocean, this is about 700 kilometers per hour. As it approaches the shore, the depth decreases. The speed drops, but the energy of the wave remains, compensating for the drop in speed with an increase in height. A wave that was a half-meter swell in the open ocean transforms into a wall of water 30, 20, or even 10 meters high as it reaches the shore. The coast doesn't have time to react. It lacks the mechanism to absorb such energy in the minutes that are available. In 2004, there was no tsunami warning system in the Indian Ocean. There was one in the Pacific. It was established after the catastrophic Chilean tsunami in 1960 and the Alaskan tsunami in 1964. The Indian Ocean was considered to be less dangerous in this regard, mistakenly, as it turned out. In Thailand, at the resort of Khao Lak, which was completely destroyed by the wave, it arrived about 70 minutes after the earthquake. This would have been enough time for evacuation if a warning system had existed, but it did not exist. On the island of Simeulue off the coast of Sumatra, directly above the epicenter, only a few people died. The locals knew their traditions concerning the smunk, tsunami, and at the first signs of retreating water, they immediately went to the hills. This oral tradition has been passed down since the time of a previous major tsunami in the area, dated around 1907. Knowledge transmitted orally through generations saved lives where modern technology could not act in time. The Sunda Trench has a history of disasters that goes significantly deeper than memory. Geological data shows that large subduction earthquakes in this area occur with a frequency of about 200 to 500 years. Tsunami deposits, layers of sand and marine debris washed inland by the wave, have been found on the coasts of Sumatra up to several kilometers from the shore. Dating of these layers points to events around the years 1308, 1530, presumably from the 17th century, and 2004. This is not a regular cycle. It's a statistical distribution where the next event could occur in 50 years or in 400. Both scenarios are equally plausible from a geological perspective, but they have radically different implications for several hundred million people living along the shores of the Indian Ocean. The very bottom of the Sunda Trench, located 7,000 meters beneath the surface, has been studied much less thoroughly than the Mariana Trench. There are several reasons for this. The trench is long and uneven, its deepest points are dispersed over thousands of kilometers, and geological activity makes the use of deep-sea equipment more challenging than in stable tectonic environments. Research conducted in the late 20th and early 21st centuries revealed a distinctive feature of the trench's floor: a thick layer of sediments, several hundred meters, accumulated over millions of years. These sediments contain preserved biological and chemical records of the history of the Indian Ocean, similar to how the rings of a tree hold climate history. Studying these sediments allows for the reconstruction of the history of subduction, tsunami events, and climate changes in the Indian Ocean over the past several million years. This knowledge is scientifically invaluable. It also means that the bottom of the trench acts as an archive, and like any archive, it follows its own rules. In the year 2021, an international expedition comprising scientists from Germany, the United Kingdom, and Indonesia conducted detailed seismic probing of the subduction zone of the Sunda Trench. The results revealed the presence of several segments of the trench with varying mechanical properties. Some segments are characterized by high friction between the plates and are potentially capable of generating megathrust earthquakes, while others slide relatively smoothly. The segment where the earthquake of 2004 occurred was retrospectively identified as belonging to the first type, with a high accumulation of stress. Neighboring segments, according to the expedition's data, also show signs of accumulated stress. This is not a prediction of an earthquake. Seismology cannot predict specific events with specific dates. It is a risk assessment, just as reliable and just as uncertain as a 3-month weather forecast. 1883, August 27th. Krakatoa, an island volcano in the Sunda Strait, not located within the trench itself but within its immediate geological system, erupted at 4:16 in the morning with such force that the sound of the explosion was heard over a distance of about 5,000 kilometers. This is a documented historical fact. Residents of Rodriguez Island in the Indian Ocean, located 4,800 kilometers away, heard cannon shots and reported it to the authorities. The explosion destroyed 2/3 of the island. Tsunamis measuring from 15 to 30 meters high struck the coasts of Java and Sumatra. Approximately 36,000 people lost their lives. The ash cloud sent enough aerosols into the stratosphere to lower the average temperature of the Earth by 0.5 degrees over the following years. This is documented by meteorological stations of that time. Sunsets around the world have become unusually red and vibrant. This phenomenon was observed by Edvard Munch from Oslo, which he captured on canvas as the famous sky in his The Scream. The Sunda Trench, therefore, played a role in creating one of the most renowned paintings in human history, although this is rarely mentioned in art galleries. After the tsunami of 2004 in the Indian Ocean, a warning system was deployed, a network of underwater pressure sensors linked to satellite buoys. The system recorded several significant tsunami-generating earthquakes after its deployment and successfully transmitted alerts, although not always in time. The issue is that for coastal areas directly above the Sunda Trench, Sumatra, West Java, the Andaman Islands, the time from an earthquake to the arrival of the wave ranges from 5 to 20 minutes. No warning system can compensate for the physics involved. The wave travels faster than evacuation can be organized. The only real protection lies in the architecture of settlements, the positioning of infrastructure away from the shore, and the culture of immediate evacuation that is instinctively integrated into the behaviors of local residents. This is what saved the people of Semilui. The Sunda Trench serves as a reminder that the deadliest depths do not kill those who descend into them. They kill those standing on the shore, unaware that the abyss is already moving in their direction. This is a particular form of danger, distant, impersonal, requiring no presence of the victim at the site of the event. Most depths in this guide, at least, require you to approach them. The Sunda Trench does not. It will come to you. Leave the Sunda Trench alone. It is greater than you, older than you, and has plans in which you play no role, except perhaps statistically. The next depth brings us back to silence and cold. But this is a different kind of cold. It is the cold of Antarctica, where the Southern Ocean hides beneath its surface the processes that govern the climate of the entire planet, and where, at depths of several thousand meters, currents are born that warm Europe and cool the tropics. We are heading to the Antarctic abyss, where thermohaline circulation begins, the world ocean conveyor, without which life on Earth would look completely different. Depth 9, the Antarctic abyss, the conveyor that keeps the world. There are things that kill you directly, by pressure, temperature, chemistry, or waves. And there are things that will kill us all at once if they stop. The Antarctic abyss belongs to the second category. It is not a place with one name and specific coordinates. It is a system, oceanographic, climatic, planetary, located in the southern latitudes of the Atlantic, Pacific, and Indian Oceans around Antarctica, at depths ranging from 2 to 5,000 meters. Here, in the darkness and cold of Antarctic waters, Antarctic bottom water is born, the densest, coldest, and most oxygen-saturated water mass in the world ocean. It descends to the depths and slowly crawls north along the bottoms of all three oceans, pushing the surrounding water masses ahead, maintaining thermohaline circulation, the very global ocean conveyor that regulates the planet's climate with a precision unmatched by any engineering structure. Thermohaline circulation is a system of global currents driven not by the wind, but by differences in water density. The density of seawater is determined by two parameters, temperature and salinity, hence thermo and halin. Cold water is denser than warm water. Salty water is denser than fresh water. In regions where the water becomes both cold and salty, it becomes so dense that it sinks, sometimes very quickly by oceanographic standards, at speeds of several centimeters per second. This phenomenon is called deep water formation and occurs in two main locations on the planet, in the North Atlantic, south of Greenland and Iceland, and in Antarctica, predominantly in the Weddell and Ross Seas. The descended water fills the depths of the oceans and slowly moves along the seabed toward the equator. In its place, waters from the depths rise to the surface, older, nutrient-rich waters accumulated over centuries spent at the bottom. This upwelling nourishes phytoplankton, which feeds zooplankton, which in turn feeds fish. The entire marine food chain largely depends on what happens in the Antarctic abyss. The Weddell Sea is a key location in this system. Located west of the Antarctic Peninsula, it is the primary region for the formation of Antarctic bottom water. In winter, air temperatures here drop to -40 degrees Celsius. The surface of the sea freezes, and when ice forms, salt is excluded from the water. The ice is almost fresh, while the water beneath becomes saltier. This cooled saline water, the densest in the world's oceans, with a temperature of about -1.8 degrees Celsius, and a salinity of about 34.6 parts per thousand, immediately sinks, descending to the bottom at a speed that is considered almost swift in oceanography. The volume of water sinking in this way in the Weddell Sea alone is estimated to be around 8 to 10 million cubic meters per second. By comparison, the flow of water in the Amazon River, the largest river in the world, is about 200,000 cubic meters per second. Antarctic deep water formation is 50 times more powerful than the Amazon. Once this water has reached the bottom, it begins its journey. Along the bottom of the Atlantic Ocean, it moves north, slowly, because the seabed is uneven and the terrain both delays and directs its path. The journey from the formation site in the Weddell Sea to the equator takes approximately 100 to 200 years. To the northern latitudes of the Atlantic, about 1,000 years. The complete cycle of the global conveyor from the point of sinking to the return to the surface is estimated to be around 1,000 to 2,000 years. This means that the water currently rising to the surface in the tropical Atlantic last descended to the depths approximately in the early medieval period. She was at the bottom while Charlemagne was building his empire. She continued to lie there while the Crusaders were marching to Jerusalem. She began to rise around the time Columbus crossed the Atlantic, and now, here she is. The Antarctic abyss is literally perilous for researchers due to reasons that combine all the best features of the previous 8 depths in our guide. Depths here reach 5,500 meters in the Weddell and Amundsen basins, with pressure at about 550 atmospheres respectively. The water temperature at the bottom is minus 1.8 degrees Celsius, which poses a constant threat of embrittlement for certain alloys when exposed for prolonged periods. The ice cover over significant portions of the Weddell Sea is permanent, multi-year, and can be several meters thick, creating the same problem as in the Arctic. The way to the surface is blocked. For a submarine or a bathyscaphe experiencing a malfunction at several thousand meters below the ice cover, surfacing is not an option in a literal sense. There is no surface to rise to. There is ice. Ice has no hatches. The price of Antarctic research in the 20th century is one that is difficult to fully comprehend. Shackleton, Scott. Amundsen, the survivor in Antarctica, perished in the Arctic. Scott's expedition to the South Pole in 1911-12 ended with the deaths of all 5 members of the final push to the pole on their way back. They reached the pole only to discover that Amundsen had preceded them by 34 days. On the return journey, they were struck by the Antarctic winter, temperatures dropping to minus 40 degrees, blizzards, exhaustion. The last diary entry from Scott is dated March 29, 1912. Their bodies were found 8 months later, 11 kilometers from the food depot they failed to reach. This is not a maritime story, but it is a story of the same system we study. Antarctica kills in a comprehensive manner, without distinguishing between surface and underwater victims. Scientific stations along the Weddell Sea and the Antarctic Peninsula operate under conditions that safety engineers in other industries would deem unacceptable. The American McMurdo Station, the largest Antarctic station, is situated on the shores of McMurdo Sound, another key area for deep water formation. The British Haley Station is located on the Brunt ice shelf in the Weddell Sea, that is, literally on the ice floating on the surface of the very sea where deep water is formed. The ice shelf moves. The station occasionally has to be relocated because its current position becomes too close to a crack, threatening to calve off part of the ice mass. In 2017, Haley Station was moved 23 kilometers for that very reason. This is not an interesting fact about Antarctic research. This is a polar station that moves like furniture because the floor beneath it is disappearing. The climatic significance of the Antarctic abyss and thermohaline circulation is the subject of one of the most serious scientific discussions of our time. Observational data shows that over the last few decades, Antarctic bottom water has become less dense due to the melting of Antarctic glaciers, which adds fresh water to the Weddell Sea and reduces the salinity of surface waters. Less dense water sinks more slowly, or it may not sink at all. The slowing of thermohaline circulation, a phenomenon documented by measurements, means changes in climatic conditions in Europe and the North Atlantic shifts in nutrient distribution in the oceans, and alterations in monsoon patterns in the tropics. None of these changes occur immediately. We are talking about processes with timescales from decades to centuries, but the direction has been set. An article published in the journal Nature Climate Change in the year 2023 by a group of scientists from the Australian National University, led by Kathy Gwynne, showed that the volume of Antarctic bottom water produced in the Weddell Sea has decreased by approximately 30% since the 1980s. 30% of 8 to 10 million cubic meters per second is an enormous amount of water that is no longer sinking to the bottom. It is an enormous amount of oxygen that is no longer delivered to the deep sea. It is an enormous amount of nutrients that is no longer rising to the surface in tropical regions. Models predict a further reduction by the end of the century, if current warming trends continue, of up to 50% of the volume from the 1980s. When a nuclear physicist wants to explain to people what a nuclear reaction is, they often use an analogy with a campfire. Slow down the reaction, you get heat. Stop it, the reactor shuts down. When an oceanographer wants to explain the significance of thermohaline circulation, they put it simply. Without it, London would have a climate like that of Labrador. Labrador is at the same latitude as London, but the Gulf Stream, which is part of the same thermohaline system, carries warmth from the tropical Atlantic northward, warming Western Europe by about 5 to 10 degrees compared to what the climate would be like without it. 5 to 10 degrees is the difference between a temperate climate and a subarctic climate. It is the difference in agricultural potential, population density, and the history of civilization. Ultimately, it is the difference in whether European civilization developed as it did or in another way. The Antarctic abyss is a place where you cannot be, cannot survive, and yet it provides the conditions for your existence on the surface. This is a paradox that most people are never aware of. We are warmed by a system initiated in darkness and cold at a depth of 5,000 meters. We breathe oxygen, part of which was produced by phytoplankton that was nourished by nutrients brought up from the depths of the Antarctic oceans. We eat fish that were sustained by the productivity created by the circulation that begins here. The Antarctic abyss is not trying to kill you. In some sense, it supports you. Just not personally, and not intentionally. Leave the Weddell Sea alone, not because it is dangerous to you, although it is, but because it is busy with important work in which your presence is a distraction. The next depth is of an entirely different nature. We transition from the global to the local, from a system that encompasses the whole ocean to a place that fits on a map as a small spot. But this spot has killed people with remarkable consistency, not through tsunamis, not through pressure, and not through cold, but by what is directly in the water, called a word that means one thing in chemistry, and in the context of Dean's Blue Hole in the Bahamas, means something entirely different. We are heading to where divers disappear so quietly that sometimes they are never found. Depth 10, Dean's Blue Hole and the underwater caves of the Bahamian archipelago, silence from which there is no return. There are places that kill loudly, through explosions, waves, collapses, pressure. And there are places that kill in complete silence, without warning, without struggle, almost without a trace. Dean's Blue Hole on Long Island in the Bahamian archipelago belongs to the second category with such consistency that locals have long since ceased to be surprised. It is a vertical underwater cave about 25 meters in diameter at the surface and 202 meters deep, the deepest known marine blue hole on the planet, listed in the Guinness World Records and visited by divers from all over the world with enviable regularity. Some of these divers return. Some do not. The ratio is eloquent enough for local authorities to periodically consider imposing access restrictions, not eloquent enough for such restrictions to be enacted. The blue holes of the Bahamas are karst formations that emerged during the last glacial maximum about 20,000 years ago when the sea level was 120 to 130 meters lower than today. The Bahamian archipelago then represented not islands but a single plateau, an extensive landmass of limestone raised above the level of the ocean that existed at the time. Rainwater, seeping through the limestone, dissolved it, calcium carbonate dissolves in slightly acidic rainwater saturated with carbon dioxide. Thus, caves were formed, horizontal tunnels, chambers, corridors, extending deep into the rock for kilometers. When the glaciers melted and the ocean level rose, these caves became submerged. Some of them collapsed, creating vertical shafts, blue holes, visible from the surface as dark circles in the light water. What you see when looking down into a blue hole is not just depth, it is a submerged cave labyrinth, extending horizontally in all directions from the vertical entrance shaft, sometimes for distances of several kilometers. Dean's blue hole appears from the surface as a perfect dark blue circle in a lagoon of turquoise water. The water near the shore is light, shallow, and warm, around 30 degrees in the summer months. It gradually darkens as it approaches the hole because the depth increases. Then, suddenly, within just a few meters from the edge, it drops off and becomes almost black. This contrast is so sharp and unexpected from above that most people's first reaction is the urge to dive in. It is precisely this reaction that leads to the most fatalities among divers in similar locations. Several factors work in combination here with such efficiency that one could assume an intention, if karst caves had intentions. The first is the topography. The vertical entrance shaft of Dean's Blue Hole expands at about 20 meters deep into a horizontal cave of significantly larger diameter. At depths between 30 and 60 meters, side tunnels branch off from the walls. A diver entering the Blue Hole without special cave training finds themselves in a three-dimensional maze where the direction up does not always lead to the exit. If you swim horizontally into a side tunnel and then turn around, you will see the same darkness in both directions. Visibility in the dark side tunnels without artificial lighting is zero. A flashlight illuminates just a few meters. Beyond those meters lies darkness and limestone. The second factor is gas chemistry. Dean's Blue Hole has a pronounced chemocline, a boundary between two layers of water with different chemical compositions at around 90 meters deep. Above the chemocline, the water is saturated with oxygen and clear. Below it, the water is almost anoxic and contains a high concentration of hydrogen sulfide. Hydrogen sulfide in the water is visible. It forms a milky white layer, the halocline cloud, which appears like mist or smoke in the light of a flashlight. A diver who descends through this layer finds themselves in an environment where visibility drops to almost zero at the transition boundary, and then it improves in the anoxic layer below. This can be disorienting. It also means that any sediment stirred up by the diver's movement from the bottom or the walls of the tunnel turns the water around them into an impenetrable cloud of suspended particles reflecting their own flashlight back like car headlights in thick fog. The third and most technically complex factor is nitrogen narcosis. At depths of 40 meters and below, the nitrogen in the air that the diver breathes begins to exert a narcotic effect on the central nervous system. This effect increases with depth and varies individually, but at depths around 60 to 80 meters, most divers experience impaired judgment, slowed reactions, and a false sense of comfort and confidence, what divers call depth intoxication, or the joys of depth. Jacques-Yves Cousteau, who described this phenomenon in 1943, called it ivresse de profondeur, intoxication by depth. He described the desire to remove his mouthpiece and share air with the fish, simply out of a sense of universal brotherhood that envelops one at great depths. A diver affected by nitrogen narcosis at a depth of 60 meters in a dark cave tunnel with no waypoints and a limited air supply is a person whose own nervous system is lying to him about how everything is going. Typically, things are not going well at all at that moment. The Blue Hole of Dean and the Lucayan cave system on Grand Bahama are among the locations with the highest concentration of diver fatalities in the world. It is difficult to compile exact statistics because some bodies have never been found, the tunnels extend far, and bodies remain there. According to the Diamond Cave Diving Organization, which specializes in cave diving in the Bahamas, over 100 divers have perished in the Lucayan cave system from the 1970s to the present day. That's one location, 100 people. Most of them are experienced divers, well-trained, equipped, and aware of the dangers. Knowledge of danger does not provide protection from it. especially when the nervous system at a depth of 80 meters sincerely assures you that everything is under control. In 1989, American diver Parker Turner tragically died within the Lucayan cave system, an experienced technical diver with several years of cave diving experience. His body was found a few days later in a side tunnel at a depth of about 70 meters, approximately 120 meters horizontally from the entrance. An analysis of his equipment showed that he had run out of air. His guideline, a mandatory piece of equipment for cave divers, a spool of line that is unwound upon entering the cave for guiding a safe exit, was broken. The exact point and manner of where it broke remains unknown. Without the line in a horizontal tunnel at 70 meters with zero visibility, finding the exit is nearly impossible. This rule, no line, no entry, is the first principle of cave diving. Turner knew it. Nevertheless, in 2002, a skeleton was found in the Blue Hole on Abaco Island, identified by his gear as Italian diver Mauro Pellicari, one of the most renowned freedivers in the world, a multi-time record holder for breath hold diving. He went into the Blue Hole to train, alone, common practice for experienced freedivers. He was discovered at a depth of about 72 meters. The presumed cause of death was a blackout due to hypoxia during ascent. When freediving at great depths, the partial pressure of oxygen in the lungs initially increases during descent, allowing divers to go deeper without the urge to breathe. But upon ascent, it drops sharply, causing loss of consciousness without any prior sensations. The diver loses consciousness just a few meters from the surface and drowns. This is known as shallow water blackout, even though it occurs after diving to great depths. The body continues to rise after losing consciousness, or it doesn't, getting stuck in the cave passage. In the case of Pellicari, it did not continue. The Lucayan cave system is also archaeologically significant. In the submerged caves of the Bahamas, remains of Pleistocene-era animals have been found, large flightless birds, turtles, and rodents that once inhabited the Bahama Plateau when it was land. This is a unique museum of prehistoric fauna, preserved under conditions of anoxic brine. Here, remains of pre-Columbian people have also been discovered, members of the Lucayan culture who lived in the Bahamas before the arrival of Europeans. The Lucayans believed that blue holes were entrances to the underworld, a world of death. This is not just a mythological concept. It is an accurate description of the place's function, adjusted for the fact that mythology was unaware of nitrogen narcosis and the chemocline, but intuitively arrived at the correct conclusion: those who enter do not return. In the 90s and 2000s, several expeditions to map the cave systems of the Bahamian archipelago determined that the total length of documented underwater tunnels in this region exceeds 1,000 kilometers. 1,000 kilometers of underwater cave tunnels, mostly in conditions of partial or zero visibility, at depths ranging from a few meters to 150, featuring chemoclines and lateral branches. Every year, several new tunnels are added to this map. Every year, several divers do not return from those already marked. What sets the blue holes of the Bahamas apart from most other sites in this guide is their deceptive accessibility. The Challenger Deep requires a multi-million-dollar submersible. The hydrothermal vents of the Mid-Atlantic Ridge call for a research vessel and specialized equipment. Dean's Blue Hole requires only scuba gear, a mask, and fins. Its depth of 202 meters is a record, but lateral tunnels begin at just 20. It is a place technically accessible to any diver with a basic certification, and this is its most deadly trait. It doesn't look like a place for specialists. It looks inviting for tourists. The water is turquoise. The sun is bright. The hole is dark and deep, but small, 25 meters in diameter. It doesn't seem frightening. It seems beautiful, right until it stops being so. Leave Dean's Blue Hole alone, not because it is deep, at least by the standards of this guide. 202 meters is almost shallow, but because it is quiet, dark, confusing, and completely indifferent to whether you make it out or not. Its guiding thread, if you take it, leads you back to the light. Its walls, if you lose it, also lead somewhere, just not where you want to go. The next depth leaves the warm Bahamas and moves into waters that, biologically speaking, are among the most teeming with life in the world. and this is their greatest danger. We are heading into the waters of the Drake Passage and the Antarctic Peninsula, where the ocean moves faster, colder, and more violently than anywhere else in the world, and where the only creatures that feel at home here have beaks, fins, and a habit of observing everything with an air of absolute superiority. Depth 11, the Drake Passage, the most angry waters on the planet. There are places where the ocean is simply dangerous, and there are places where the ocean is furious, methodically, constantly, without pauses or weekends. The Drake Passage, situated between the southern tip of South America and the Antarctic Peninsula, belongs to the latter category so convincingly that sailors for 4 centuries have referred to it by various names, but always with a respect bordering on superstitious fear. Gates of Hell, Devil's Sea, Roaring Forties, Furious Fifties, Screaming Sixties. These are not poetic metaphors, but practical terms that sailors use to designate the latitudes through which the passage runs. This is working terminology from professionals who deal with a phenomenon for which there is no neutral description. The Drake Passage is named after the English privateer Francis Drake, whose ship was swept far to the south by a storm in 1578 after passing through the Strait of Magellan, and thus accidentally discovered the existence of open water between the Americas and Antarctica. Drake did not intentionally cross the passage. He was swept there, against his will. This fundamental distinction characterizes the relationship that most sailors have had with this location for centuries. The first to consciously navigate the passage from east to west was the Spanish explorer Francisco de Orellana in 1600, a journey that entered the history of navigation as one of the most challenging documented crossings of that era. The width of the Drake Passage is about 800 to 1,000 kilometers at its narrowest point. It is the widest strait on the planet, and it is this width that creates what happens here. The Antarctic Circumpolar Current, the most powerful ocean current on Earth, flows around Antarctica from west to east continuously, with no land to stop or divert it for several million years, since tectonic forces separated Antarctica from South America, opening the passage. The volume of water carried by this current through the Drake Passage every second is approximately 170 million cubic meters. This is 1,000 times the total discharge of all the rivers on Earth. It is 700 times greater than the Amazon River. All of this water is squeezed through a passage 800 kilometers wide, and the compression that occurs here is what makes the Drake Passage what it is. The western winds in the southern latitudes blow unobstructed. There is no land to stop them, except for Antarctica itself. They circle the planet continuously, gaining speed and energy over thousands of kilometers of open ocean. By the time they reach the Drake Passage, they carry waves that have formed along the entire route from the Indian Ocean through the Pacific. Wave heights in the Drake Passage during a strong storm regularly reach 15 to 20 meters. These are not record values. Historically, waves higher than 30 meters have been recorded in this area. Periodic waves reach heights at which they are referred to as killer waves, abnormally high solitary waves arising from the nonlinear interaction of several wave systems. A killer wave measuring 25 to 30 meters, moving in a storm at about 70 kilometers per hour, is a force that even modern vessels struggle to handle, and historically, wooden ships were completely at their mercy. The depths of the Drake Passage vary from 3 to 4,500 meters in the main part, and are significantly shallower near the underwater ridges, the Scotia Ridge and the Drake Ridge, which cross the passage in several places. These ridges are not visible from the surface. They lie at depths of 500 to 2,000 meters beneath the keel. However, they significantly influence the hydrology of the passage. The water rising over the ridges creates zones of turbulence and upwelling, the rising of cold, deep waters, which interact with surface currents and create unpredictable local conditions. A captain who knows the course through the passage by heart may find themselves in a situation that the chart did not predict, because the hydrology of the passage changes depending on the season, the phase of currents, atmospheric pressure, and dozens of other factors interacting non-linearly. The water temperature in the Drake Passage during summer is around 2 to 4 degrees above zero. In winter, it is about zero or slightly below. This means that a person who finds themselves in the water without safety gear loses mobility after about 10 to 15 minutes and suffers from hypothermia within 30 to 40 minutes. In a storm, the swell is so severe that a normal lifeboat is practically unmanageable. An inflatable life raft in a storm in the Drake Passage is essentially a device that technically keeps you above water, and nothing more. It is carried wherever it may go. In the Drake Passage, wherever it may go means eastward, along the current, into the open Atlantic Ocean. The history of shipwrecks in the Drake Passage begins with the first European expeditions to Cape Horn and represents one of the darkest chapters in human maritime history. Cape Horn, a rocky promontory on Horn Island at the very southern tip of Chile, is the western entry point to the passage and a landmark around which sailing ships had to navigate the southern end of America to transition from the Atlantic Ocean to the Pacific. This was the standard trade route until the opening of the Panama Canal in 1914. In its 3.5-century existence, over 800 documented ships have wrecked at Cape Horn, though the actual number is much higher, as many ships have vanished without a trace. Only in the 19th century, around 10,000 sailors perished at Cape Horn. That is more than in most naval battles of that century. In 1872, the American clipper Duke of Alba attempted to navigate Cape Horn from east to west, the most difficult route, against the prevailing winds and currents. The vessel spent 42 days trying to round the Cape, gaining a few miles each day only to lose them again to the next storm. Ultimately, the captain decided to turn the ship around and sail around the world another way, through the Indian Ocean and past Cape of Good Hope, adding several thousand miles to the journey. This decision, made after 42 days of battling the Drake Passage, was not considered a capitulation. It was deemed sensible. Modern expedition vessels regularly sailing to Antarctica through the Drake Passage are equipped with specially reinforced ice-class hulls, stabilizers, ballast systems, and meteorological support. Nevertheless, the Drake's disease phenomenon, where nearly all passengers on a vessel crossing the passage for the first time suffer from seasickness for 2 to 3 days, has become such a universal experience that it is mentioned in tourist descriptions of Antarctic cruises as a matter of course. Tourist brochures write about it with delicate restraint. The crossing of the Drake Passage may be unsettled. This is about as accurate as calling the fall of Pompeii an unfortunate weather event. Biologically, the Drake Passage is one of the most productive areas of the world's oceans. Upwelling over underwater ridges brings nutrients up from the bottom, nourishing vast populations of krill, tiny crustaceans measuring 2 to 5 centimeters long, which form the base of the Southern Ocean food chain. The biomass of Antarctic krill is estimated to be around 300 to 500 million tons, one of the largest biological resources on the planet. Blue whales, humpback whales, fin whales, crab-eater seals, penguins, albatrosses, and petrels all feed on krill. This abundance of life is concentrated in waters that can kill a human in 30 minutes during a storm. Nature sees no contradiction in this. The albatrosses of the Drake Passage deserve special mention, not as a threat, but as witnesses. The wandering albatross, with a wingspan of up to 3.5 meters, the largest flying bird on the planet, spends a significant portion of its life in the Drake Passage and surrounding waters. Young albatrosses, after leaving their nests on South Georgia or Crozet Islands, spend up to 8 continuous years in the air over the Southern Ocean, not landing at all, sleeping in flight. They utilize the storm winds of the Drake Passage for dynamic soaring, where the bird gains altitude in rising air currents over the crest of a wave and glides down the leeward slope, using the wind speed differential. A storm that means death for humans signifies a tailwind for the albatross. This is perhaps the most accurate illustration of just how the Drake Passage is not a hostile place, but simply an area not designed for humans. In the year 2019, the Argentine research vessel Primavera encountered a storm in the Drake Passage while en route to the Antarctic Peninsula. Wave heights reached 18 meters. The vessel sustained damage to its superstructure. 2 crew members were injured. The ship made it to the Antarctic base under its own power. This is considered a relatively fortunate outcome. Several years earlier, the Norwegian tourist ship Explorer sank in Antarctic waters after sustaining a breach, presumably from contact with ice. All 154 passengers and crew members were evacuated. This is also deemed a fortunate outcome. The measure of fortune in the Drake Passage operates differently than in most other places. The Drake Passage is the only location in this guide where danger is concentrated not at the bottom or in depth, but at the surface. Waves kill here without requiring immersion. Cold kills without the need for pressure. Wind kills simply by existing. This is a democratic deadliness, accessible to anyone who finds themselves here, regardless of the depth at which they are located. The surface of the Drake Passage is more dangerous than the bottom of most calm seas. This turns the entire logic of our guide on its head, and yet it remains true. Leave the Drake Passage alone. Not because it is unreachable, people regularly traverse it and most make it to the other side. Just remember that most does not mean all. And the Drake Passage, methodically, storm after storm, generation after generation, reminds us of this difference. The next depth brings us back to where we began, back to the Pacific Ring of Fire, to tectonics and volcanism. But this time, we are not heading to a caldera or a subduction trench. We are going to a place that combines features of several previous depths simultaneously: volcanic activity, extreme depths, biological anomalies, and a history of exploration where luck has played a role no less significant than science. We are going to the Tonga Trench, the second deepest point in the ocean, and to what lives in its absolute darkness. Depth 12, the Tonga Trench, the second bottom of the Earth, and viruses from the abyss. If the Challenger Deep is an absolute record, solemnly documented, then the Tonga Trench is its restless younger brother, dwelling in the shadow of the elder, but compensating for its relative obscurity with being significantly more geologically active, biologically strange, and, by some measures, scientifically more alarming. The Tonga Trench is located in the southwest Pacific Ocean, east of the Tonga Archipelago, and represents the northern section of the Tonga-Kermadec Trench, a system stretching approximately 2,500 kilometers from north to south. The maximum depth of the trench is approximately 10,820 meters at a point known as the Deep Horizon. That is about 100 meters shallower than the Challenger Deep, making it the second deepest point in the world's oceans. A 100-meter difference may sound like a minor consolation in absolute terms, but in reality, it represents the distinction between the deepest and the second deepest, a difference that holds significant meaning in scientific publications and means absolutely nothing in terms of survival. The Tonga-Kermadec Trench is a result of the subduction of the Pacific Plate beneath the Indo-Australian Plate, a process that occurs here at one of the highest recorded subduction rates on the planet, around 24 centimeters per year. This is nearly 4 times faster than in the Sunda Trench. This means that geological activity here is more intense, earthquakes are more frequent, and volcanic activity on the associated island arc is more vigorous. The Tonga archipelago consists of over 170 islands, some of which are active volcanoes. In January 2022, the underwater volcano Hunga Tonga Hunga Ha'apai, located about 65 kilometers north of the main island of the archipelago, erupted with such force that the explosion was recorded by seismographs worldwide. A pressure wave circled the Earth several times, and a tsunami spread across the entire Pacific Ocean. Scientists estimate this was the largest volcanic eruption in the last 30 years. A plume of ash rose to about 57 kilometers, higher than most known volcanic emissions in recent history. The Tonga archipelago was partially isolated from the outside world for several days due to damage to the only underwater communications cable. This did not happen in some remote and sparsely populated area. It occurred near inhabited islands, close to people. The Tonga Trench is not a relic of the past. It is active right now. The biology of the Tonga Trench is studied in several respects better than that of the Challenger Deep, partly because it is easier to reach from Australia and New Zealand, and partly because its biological diversity proved so unexpected that several significant expeditions were directed here. In 2012, a New Zealand expedition from NIWA, the National Institute of Water and Atmospheric Research, conducted a series of trawls and photographic surveys at various depths of the trench. Images and samples of creatures were obtained, some of which could not be immediately classified. Among the documented finds were several species of amphipods previously unknown to science, reaching sizes of 34 centimeters, which is phenomenal for such types of crustaceans. These super amphipods were informally dubbed giant sea fleas in the press, a name that biologists have used with undisguised annoyance, yet it has found its place in popular descriptions. Giantism in deep-sea conditions, a phenomenon known to biologists as deep-sea gigantism or abyssal gigantism, is associated with several factors, none of which has been definitively established as the sole cause. It is believed that low temperatures slow down metabolism, allowing organisms to grow longer without reaching sexual maturity. High pressure influences cellular processes in certain ways, and limited food resources favor organisms with larger bodies capable of storing energy in fat reserves. Most likely, a combination of all these factors is at work. The result is clear. The common isopod in shallow waters measures about 1 centimeter. Baphinomus giganteus, a deep-sea isopod, can grow to 75 centimeters in length. They belong to the same family of organisms, with the only difference being their habitat depth and several million years of evolutionary adaptation. However, the most scientifically significant discovery made in the Tonga-Kermadec Trench over the past 2 decades was not the discovery of a new animal species or a new geological structure. It was a finding related to viruses, and it has changed the understanding of what is happening in deep-sea sediments much deeper than previously thought. In 2019, an international group of scientists published in the journal Nature the results of an analysis of sediment samples taken from the bottom of the Tonga Trench at depths ranging from 6,000 to 11,000 meters. These samples revealed the presence of viral particles in concentrations that the researchers themselves described as unexpectedly high. The concentration of viruses in the sediments of the deep-sea trench ranged from 800 to 900 billion viral particles per square centimeter, 10 times more than in comparable sediments at intermediate depths. This indicates that trenches act as traps for viruses. Organic particles to which viral particles attach sink and concentrate specifically in the deepest parts of the ocean. Viruses in deep-sea sediments perform a function that scientists refer to as the viral shunt in oceanic ecosystems. They infect bacteria, destroy their cells, and release dissolved organic compounds that would otherwise remain locked inside the cells. This accelerates the biogeochemical cycle, the turnover of carbon, nitrogen, and phosphorus in deep-sea sediments. In other words, viruses at the bottom of the Tonga Trench are active participants in the global carbon cycle. This is not an intuitively obvious conclusion. Most people think of viruses as pathogens rather than as geochemical agents. Nonetheless, on a planetary scale, the viral shunt in deep-sea sediments is a significant factor in the balance of carbon between the ocean and the atmosphere. In 1998, the American submarine House, a converted research vessel, made a dive into the Tonga Trench as part of a program to study seismic activity. At a depth of approximately 8,000 meters, the device recorded a series of acoustic anomalies, short, intense, low-frequency pulses that did not match any known biological sources or identified geological ones. The recording was transmitted to the NOAA Acoustic Laboratory. Analysis revealed that the source was located several kilometers away from the device, in a horizontal direction rather than below. The final identification of the source in the report was marked as likely biological, species unknown. This is a standard phrase in oceanographic reports for cases where measurements have been made, but interpretation is impossible. In the Tonga Trench, several dozen such recordings have been accumulated. Many of them still lack an established source. In 2023, an American expedition aboard the vessel Falkor conducted detailed video footage of the seafloor of the Tonga Trench at depths ranging from 8,000 to 10,500 meters. Among the documented findings were several species of snailfish from the genus Pseudoliparus, which inhabit only these depths. Snailfish are the deepest known vertebrates, with a recorded depth for a vertebrate animal noted in the Tonga Trench of around 8,336 meters. This means that vertebrate animals, those with a backbone, including humans, are capable of existing under pressures exceeding 800 atmospheres. The snailfish appears rather unimpressive, pinkish, semi-transparent, around 20 centimeters long, with a soft body and disproportionately large head. It swims near the bottom and feeds on amphipods. Nothing fearsome, just an organism quietly living where every square centimeter of its body bears a load of 80 kilograms. Evolution makes the impossible routine given enough time. The Tonga archipelago has a unique cultural relationship with the sea, which is not surprising for a people living on islands amidst one of the planet's deepest ocean trenches. The Polynesian tradition of navigation, shared by Tongans with Hawaiians, Maori, and Samoans, is one of the most developed navigational traditions of pre-industrial humanity. Polynesian navigators crossed the Pacific Ocean without compasses or maps, using stars, wave direction, bird and fish behavior, watercolor, and wind temperature. They likely knew of the trench, not as a geological structure, but as a place where the water is dark, the fish are unusual, and the depth seems infinite. Their navigational wisdom included not only knowledge of where to sail, but also knowledge of where not to dive. This latter knowledge seems to have been learned quite quickly. The Tonga Trench is a place where geological activity, biological anomalies, and viral ecology converge in one point, creating something that is hard to define with a single word. This is not just a deep place, it's a dynamic system, where something significant happens every few years: a volcanic eruption, a major earthquake, the discovery of a new species, an unexpected acoustic anomaly. It's a location with a biography, not dull and static as one would expect from a deep abyss, but alive and unpredictable. Perhaps making it more concerning than the Challenger Deep, at least that doesn't surprise us. The Tonga Trench surprises us regularly. Leave the Tonga Trench be. Not because nothing happens there. Things are constantly occurring. That's precisely the point. We arrive at the last chapter of our guide. The 13th depth. Not the deepest and not the hottest. It doesn't produce tsunamis or boil in acid. It kills differently, slowly, imperceptibly, in a way that leaves no traces recognizable to the untrained observer. This is the dead zone, a hypoxic zone in the Gulf of Mexico and dozens of similar places around the world, where the ocean dies quietly, without drama or spectacle, and where the cause of death is not geology or physics, but humanity itself. This is the final and perhaps the most uncomfortable chapter of our guide. Depth 13, Dead Zones, the abyss we created ourselves. The 12 previous depths of this guide share one common feature. They existed before humanity, they exist with humanity, and they will exist after humanity. The Challenger Deep does not require us to be an abyss. Hydrothermal vents boil independently of whether anyone is watching or not. The Drake Passage storms with the same fervor in the absence of witnesses as it does in their presence. These are old, autonomous, self-sustaining systems, dangerous by the nature of their geology, physics, or chemistry, but not by human will. The 13th depth is different. It was created by us. Not intentionally, which might be worse than it were intentional. Intentional evil at least implies awareness. This is not. It is a byproduct. It is what happens when civilization operates precisely as it is supposed to, and that becomes the problem. Dead zones. Hypoxic and anoxic zones of the ocean floor are areas of the ocean where the concentration of dissolved oxygen has dropped to levels at which most marine organisms cannot survive. The boundary is defined quite clearly. Below 2 milligrams of oxygen per liter of water, this is hypoxia, low oxygen. Below 50% saturation, this is a serious disruption. 0. This is an anaerobic zone, a dead zone in the literal sense. Fish flee, if they can get away in time. Bottom-dwelling organisms that cannot escape, worms, bivalves, echinoderms, crabs, perish. Bacteria that use other oxidizers instead of oxygen thrive, producing hydrogen sulfide, methane, and carbon dioxide. The seabed turns gray, covered with bacterial mats, empty of everything we are accustomed to calling marine life. This is the dead zone. According to the World Register of Marine Species and the National Oceanic and Atmospheric Administration of the United States, by the 20s of the 21st century, there are over 500 documented dead zones on the planet. 500 is not a rare anomaly. It is a global pattern distributed along the coastlines of all inhabited continents. Some of them are seasonal, appearing in the summer and recovering by autumn. Some are permanent, existing for decades. Some are expanding. Most are expanding. The largest dead zone in the Western Hemisphere is located in the Gulf of Mexico, at the mouth of the Mississippi River, and annually covers an area of between 15,000 and 20,000 square kilometers during the summer months. This is roughly the size of the state of Connecticut, or Israel. Every summer, regularly, with astonishing predictability. The mechanism of its formation is classic eutrophication. The Mississippi gathers runoff from agricultural lands in the central states of America, saturated with nitrogen and phosphorus from fertilizers, and carries it into the Gulf of Mexico. Nitrogen and phosphorus are nutrients. In the Gulf of Mexico, they feed not fish or corals, they feed phytoplankton. Phytoplankton explosively reproduces, creating what are known as blooms, mass outbreaks of algae that color the water green, brown, or red. When the biomass of phytoplankton reaches its peak, it begins to die off. Bacteria break down the dead organic matter, and in this process they consume oxygen, all the oxygen. The bottom layer of water becomes depleted of oxygen. Fish, crabs, and shrimp that are not affected by the oxygen depletion in the upper layers either die or flee. Commercial fishing in the Gulf of Mexico incurs annual losses directly related to the dead zone. Populations of bottom fish, brown shrimp, and blue crabs are declining in areas where the dead zone overlaps traditional fishing grounds. Fishermen, whose families have fished these waters for generations, are finding empty nets where once their nets were filled with catches. This is not an ecological abstraction, it is specific economic losses for specific people, measurable in dollars and in fish. According to estimates from the National Marine Fisheries Service of the United States, the economic damage from the dead zone in the Gulf of Mexico amounts to hundreds of millions of dollars each year. The cause of this damage is the fertilizers used on corn and soybean fields in Iowa, Illinois, and Indiana. The distance between the field and the dead zone is thousands of kilometers of river. The link between them is direct and documented. The Baltic Sea is the European equivalent of the Mexican situation, only worse in scale and duration. Dead zones in the Baltic have existed and were documented as far back as the mid-20th century, but their area has significantly increased in the second half of the century. Today, around 8,000 square kilometers of the Baltic Sea floor are covered by permanent dead zones. This is more than 2% of the entire area of the sea. In the central basins, Gotland and Bornholm, oxygen depletion in the bottom layers is a chronic issue and does not recover naturally due to the specific hydrology of the Baltic Sea. It is almost a closed basin with limited water exchange with the North Sea. Oxygen reaches the depths of the Baltic only during rare salinity intrusions, when dense saline water from the North Sea breaks through the Danish Straits and ventilates the bottom layers. Such intrusions occur irregularly, once every few years under specific wind and atmospheric conditions, and each time they are accompanied by a brief revival of the bottom ecosystems, until the next oxygen crisis. Geological data show that dead zones in the Baltic have existed even in prehistoric times, under conditions of natural climate warming. However, their current persistence and extent are anthropogenic. Runoff of fertilizers from agricultural lands in 9 countries bordering the Baltic, plus wastewater from dozens of cities, create a nutrient load that the sea cannot process. Swedish, Finnish, Estonian, Polish, and German scientists document this process with a meticulousness deserving of better application, because observing a disaster and stopping it are different tasks, requiring different political and economic efforts. The Black Sea is a part of the world ocean that is less often discussed in the context of dead zones, even though it is the largest natural anoxic basin on the planet. Below a depth of about 150 meters, the Black Sea is virtually devoid of oxygen. This is not an anthropogenic phenomenon. It is the result of natural stratification. The surface waters, freshened by the runoff of major rivers, the Danube, Dnieper, and Don, are too light to sink and ventilate the depths. The deep waters, saturated with hydrogen sulfide, have existed in this state for thousands of years. Most large marine animals inhabit only the upper 150 meters. Below that, only anaerobic bacteria and chemosynthetic microorganisms survive. The bottom of the Black Sea at depths exceeding 200 meters is literally dead, due to lack of oxygen, not life. Medieval shipwrecks remain remarkably well preserved there, precisely because the anaerobic environment prevents the activity of wood-boring insects and decomposing bacteria. A Turkish expedition in 2017 discovered over 60 medieval vessels on the bottom of the Black Sea, including several dated to the early Middle Ages, in a condition that researchers described as almost untouched. Their preservation is ensured by the same mechanism that kills everything else. The death of one serves as a preservative for another. A seasonal dead zone in the Gulf of Oman was discovered and detailed in 2018 by a group of scientists using underwater glider drones. The zone turned out to be the largest documented in the open ocean, about 170,000 square kilometers of oxygen-depleted waters at depths ranging from 200 to 800 meters. Drones that spent several months in this area transmitted data about oxygen concentration, which scientists initially dismissed as equipment error due to the extremely low values recorded. However, this is not an error. This represents 1/3 of India's area covered by water, where large marine animals cannot breathe. Fish, tuna, sharks, everything that is not a microorganism is forced to either rise above 200 meters or navigate around this zone. This compresses the living space for a vast number of species into a thin surface layer. The fundamental difference between dead zones and all previous depths in our guide is that they do not directly kill humans. Instead, they kill fish, crabs, mollusks, worms, those that cannot escape. They wipe out ecosystems, a process that takes decades, not minutes, and therefore fails to produce the immediate horror effect associated with a cable snapping from a submersible or a tsunami wave. This kind of fear is different. It is slow, background, requiring not instincts but an understanding of cause and effect over distances of thousands of kilometers and timelines of years and decades. Such fear is significantly harder to grasp and even harder to act upon. In 2022, the Norwegian Institute of Marine Research published a forecast predicting that if current trends continue, by the middle of this century, the area of dead zones in the world's oceans will approximately double. This means around 1,000 documented zones instead of the current 500. This indicates a further reduction in productive areas for commercial fishing. It signifies a change in species composition in affected areas, from traditional catch species to those more tolerant of hypoxia, such as jellyfish. Jellyfish are not mentioned randomly. They tolerate oxygen depletion significantly better than most fish and invertebrates, and in dead zones, they often become the dominant species, not because they seek these areas, but because their competitors leave or perish. The jellyfish ocean is not a futuristic science fiction concept. It is a documented trend in several existing dead zones. There is an irony in the fact that the 13th and final depth of our guide is the only one that can be changed. The Challenger Deep cannot be altered. It is where tectonic forces placed it millions of years ago. Hydrothermal vents will continue to bubble as long as magma is present. The Drake Passage will remain stormy as long as the westerly winds blow. Dead zones are different. They respond to changes in nutrient load. When in the 1980s, Black Sea Basin countries reduced fertilizer use, partly due to economic hardships and partly due to conscious policy, dead zones in the northwestern Black Sea partially recovered. When the European Union imposed restrictions on phosphorus in detergents in the 90s, it reduced phosphorus loading into the coastal waters of the Baltic. Recovery occurs slowly, significantly slower degradation, but it is happening. That's the only good news in the 13 chapters of this guide. It's small, but honest. We have traversed all 13 depths, from the bottom of the Mariana Trench to the boiling vents of the Mid-Atlantic Ridge, from the Rapa Lakes at the bottom of the Gulf of Mexico to the absolute darkness of the bathypelagic zone, from the Sulphur Lake in the Hawaii Basin caldera to the icy crypt of the Nansen Basin, from the ancient salt of the Mediterranean abyss to the wave of the Sunda Trench, from the conveyor of the Antarctic abyss to the silence of the blue holes of the Bahamas, from the storms of the Drake Passage to the viruses of the Tonga Trench, and finally, to the quietest and the closest of deaths, the dead zones we have created ourselves. The ocean covers 71% of the planet's surface. Its average depth is around 3,800 meters. Its volume is about 1,370,000,000 cubic kilometers of water. We have explored less than 20% of this volume. The rest is terra incognita, only aqua. Where we have been, we found liquid sulfur, viruses in concentrations lethal to bacteria on an industrial scale, multicellular animals without oxygen, fish under pressures of 800 atmospheres, and a conveyor that regulates the climate of the entire planet. Where we have not been, there is probably even more interesting. This is exactly why people continue to dive. Not because it is safe, because it is there, and because we are a species that has always wanted more than what is on the surface. Take care of yourself. Stay on the shore. Or, if you cannot resist, at least take a guiding thread with you. The guide is closed. The abyss is not.